The universe is calling me. It speaks both day and night. It's full of dark and light, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space, fields and forms, math and voids. It all sings with one voice. It's home. Boundaries set, foundations laid. Sound was heard, matter made. Solar systems from afar. Names and numbers for the stars, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space. It's the Lord's.
Hey, welcome everybody. How are you? I'm sporting a new pair of glasses. Actually, these were sent to me by Commander Cobra, who's another KGRA host. How you guys doing? It's good to see you. Hello, Daisy and Zoe, Native NC. How you doing? Richard Spencer, thanks for coming out. Michael Hedrick's with us. Tim F. Genghis is with us. Yes, sirree. And Stuffy's here. Nice to see you guys. I'm Genghis, Snazzy Spectacles. Yeah, I mean, why not? So tonight, it's a little bit cloudy out there, but the purpose of tonight is to kind of showcase an integrated feature that we're adding into Sky Tour, and based on what you think, we'll keep it or we'll ditch it. It's up to you. Anyway, Rocket City, nice to see you. Rascally, thank you for coming. Daryl will be here in a little bit, from what I understand. And we'll make sure to bring him in when he shows up. But anyway, let's see here. So this right here, this is our friend, the 37 cluster. It looks like the number 37, doesn't it? And where it is in the sky is right here. Now that may not mean much to you, but there's Betelgeuse. See Betelgeuse? We're going to go to Betelgeuse tonight. We're going to circle around it and see what it looks like. And these are suspected ways that it actually looks. It's just a thought process based on what we know about supergiants, red supergiants. Betelgeuse is on the verge of a supernova. Its life is nearly ended. So at some point, it's going to be exploding in our night sky or daytime sky, and wherever it goes, wherever it explodes, we're going to see it in the daytime. If it explodes during the day, we'll see it during the day. When I say during the day, meaning the sun is around on that side of our seasonal sky. So the Earth's at that point in its orbit where, when we look toward the sun, Orion is near it. And so if Betelgeuse does go, we are going to see it as another star in the sky. Not nearly as bright as the sun, of course, but probably initially it could be as bright as Venus, maybe a little brighter. But in the daytime sky, it'll be very, very bright. Anyway, then it'll generally fade again. But hey, Fantasy, how's it going? So what I'm going to do now is show you again this 37 cluster. It's just to the left of Betelgeuse, as you can see in our chart there. All right, and if we start taking a picture of it, let's just do that. We'll take a 20-second photo here. Let me just move it a little bit more into the view here and drop it down a little bit. You can see those beautiful colors in it when you actually stretch out the stars. You can see these gorgeous colors. And so let's make sure that our focus is good. I did go through a focus set. Alicia, how are you? Alicia Vieras is with us. Nice to see you. Fantasy, what's going on? Is Wide World Viewer going to be live soon? I don't know the answer to that. I don't know. Are you talking about the viewer for Sky Tour live stream? To view other things, like all of the things we've done? Or are you talking about something different? All right, so let's do a 20 seconds here. And, all right, so as this has taken 20 seconds to capture, you can tell by the little yellow bar down here that indicates it's progressing. All right, and what I'm going to do is go into our live stack. All right, and while it's doing that, let's actually go and check out this guy. All right, what's this? Well, this is the 37 cluster that you're going to see as seen from the Earth. Here's the Earth, okay? And you might actually notice, let's see here. You might notice a few things if I spin this around here. Let's go this way. Okay, if we come this way, now it's not so bright. We can start to see the stars. Oh, there's our sun. But in that general direction is the 37 cluster. So what we're going to do is we're going to go there. And it's actually called NGC 2169. So as we head there, this is a full representation of the 3D universe. And we're going to go and see this cluster. Well, here it is. Now, when you're up close to it, you barely recognize it. But if we back away, okay, as you'll see, if we back away, all right, you can start to see the 37 is in there. All right. Now, this 37, all right, is a visible asterism to us. It's not real, but it's what it looks like to us. And so when you look at it, you might say, well, wait a minute. What's it look like from the other side? Well, let's go to the other side. See, this is all in 3D. This is what this cluster looks like in 3D. Isn't that crazy? Look at that. Yeah, that's pretty neat. You know, it only looks like a 37 from one particular perspective, and that's that one that we have. So there it is. That's the 37 cluster as seen if you could go to it. You know, so that's neat, and that's the kind of thing that we're going to do tonight is go visit some of these things. We're going to be checking other things out too. Okay, so for instance, right now we'll come back here, and this is the 37 cluster as we're looking at it now. But what we want to do is color correct. We got to take off our histogram processing over there, which is really bright, and then we want to take care of getting this processed just a little bit. All right, there you are. And now what we'll do is color correct it, make the blacks black. There we go. So there's our 37 cluster. See. Now, I have a big curved monitor, as I've told you before, so on the left side of my monitor is the observatory feed. At the right side is the feed from the broadcast software, so I'm using both, okay? And I'm checking to see if Daryl wants to come in. He's not here yet, so that's fine. All right, so I'm going to move a couple things out of my way here. There we are, and there we are. Okay, so the 37 cluster, we saw that and how that looks. We'll actually save it. Now, there are some light clouds, like I said, but it doesn't matter because we can actually see through the light clouds. This red is from those light clouds. All right, let me do the zoom here. I see a question out there from Michael Hedrick, and I'll get to you in 1 second. All right, so we're going to zoom this and move over, and this way we have finer control over these curves. All right, here we are. Okay, let's go see what Mike asked. Mark, this is exactly what I was hoping to see from other locations. Do we know what caused the space between the numbers? Stars. Oh, well, you know what happens, Michael, is when a cluster forms, it forms inside of a cloud of gas and dust. And so the stars form any which way they want. And some of them are slightly more massive than others, but they're generally about the same and at the same stage in their evolution initially, because they're all born at the same time. But some stars may be a little more massive. They're going to run through their hydrogen quicker than others. So you might see a red giant in there. So red giants start to pop up. That means that all the stars eventually will pop up. So that said, the distance and space between the stars was caused simply by their gravitational interaction with each other over the millions of years that the clusters existed. So it just so happens, from our point of view, as I showed you with this particular screen, it just so happens that we look at it from a particular point of view. We don't, it doesn't look like anything to us in particular, right? If we go to the Pleiades, you'll see exactly what I mean, right? It just looks this way from our one perspective, and that's cool. So, coming back to the STLS screen, all right, let's just save this. I mean, we've got 16 saved here. It's really, again, it's a cloudy night, but clusters look beautiful on a cloudy night anyway. Sometimes, you get these really soft, subtle shapes to them. The stars are soft, and it really looks pretty, and it looks like a piece of art rather than clouds in the night sky. So we try. All right. So 37 cluster, let's save it. All right, that's been saved. Let's save the exactly as seen. All right. So now we're going to go somewhere else. I haven't tried going to a great many of these objects in the other 3D program, but we'll try it and see what happens. So it'll be kind of fun. First things first, let's go up here. And in our region up here, we also have some other stars that are pretty fun to look at. And I'm going to go to those right now. It's going to be right about here. There it is. Let's check out the Pleiades. Now, we've looked at the Pleiades many times, but you haven't seen it like this. So we're going to go there now. And if you watch the telescope right here, you're going to see the telescope, taking a trip upwards. And you'll see the stars moving, and the Pleiades will soon show up in the view here. All right. There they are. So that's pretty cool. So I think what we want to do is we're going to reshape the Pleiades. We're going to get them in our view a lot better. And meanwhile, we're going to end up heading back to Earth. All right. And we're going to get to Earth, and we're going to end up here just to orient ourselves, get ourselves oriented. That's the center of the galaxy you're seeing right here. Okay. And then the sun, we go zipping by the sun, and there's the Earth. Okay, let's now do something that's very important. We're going to now search for, and it's Messier 45, which is the Pleiades designation. So M45. Okay, there we are. And that arrow points to where they are, so we can actually just sort of peek at them. And at this distance, we should be able to see them. And there they are. If you notice, there they are. We see them right now. Those are the Pleiades. And so we're going to go there now. All right, so we have gone way past light speed. You could think of it as a way to bend space. And here we are, 400 light years away. Well, there's the Pleiades, all right? There's Alcyone, we have Merope and Pleione, all these others. But now, one of the things that we can do is, in the Pleiades here, we can actually start to do this. We can circle around the Pleiades and see what it looks like from all these different perspectives. The Pleiades has somewhere... yeah, okay, Daryl's yelling at me. All right. Let me bring him in. All right, here we go. All right. Can you hear me okay, Daryl? Yeah. All right, folks, welcome Daryl to the stream. Hello, Daryl.
Hello, Daryl. Hello, Mark. Hi, everybody.
Yeah, so this is the Pleiades as we're going around it in 3D. So, and that reflection nebula that we're seeing right there, that's a reflection nebula that's probably part of a same nebula that we're in, which is kind of interesting. And this
I can't see a darn thing.
I know you can't. I gotta fix that for you. And you may have trouble. You may have to watch YouTube for this part of it, but that's okay. I can't have that screen shared as well as the observatory screen. So let me just do the share anyway for Daryl so that he's not completely left out. I hate having him left out. So let's go over here. Okay.
You'll miss me when I'm gone.
I'm not so sure, but whatever.
Yeah, whatever.
All right, let's see here. That's interesting. I'm looking for the window. Oh, here we go. There were more. This is the window you want to see. Okay. All right, so now what we're going to do is we're going to bring the Pleiades in here, and then we're going to take another photograph of them. And you can actually see all that blue dust that is scattering the starlight from the Pleiades stars. And you can see and even though it's, like I said, even though it's light clouds out there right now, It's actually not bad at the moment. There's more clouds coming, so I'm not sure how long this is going to go. Tonight's more for exploring the new 3D feature of SkyTour Livestream.
Part of their tricks.
Let's see. I can hang up on you if you'd rather.
I'm pulling your leg. Lighten up.
Well, I was pulling yours. Okay. All right. So as you saw, you all saw, it's actually interesting. Let me just do one more thing here. Kind of a just one little thing here. I got to change some settings here. All right. Anyway, what we're gonna do is we have our guide star. We're guiding now. So what I'm gonna do is I'm actually gonna do a 25-second shot of this, and then we'll come back into our amazing live stack, which always shows us beautiful views. And the last one was the 37 cluster, which we saw here. I'll get rid of our second histogram, and now we're clear here for the first shot, and this will be the Pleiades. This is Messier 45, by the way, M45.
There. Now I'm set.
You're set. What'd you do?
I've got everything set up on my screen. I got pop-up chat over on the right side. And
Oh, good.
just like the good old days.
Excellent. Yeah,
That is a nice picture.
yeah, I mean, through the light clouds, it's not bad. And it's only one frame right now. So we've got two frames stacked now, and that actually what I can do now to even enhance this further, I'm going to do something called color noise reduction. Once I click this button right there, you see it. Watch what happens on the screen. Watch the difference. Ready? Here we go. Look at that. It reduces a lot of the noise in between, and I still have to do a color correction here. All right, and I still have to pull this back. This is our darks, because there's actually a lot more dust visible here. Look at all this dust that's visible. Incredible. I dare say that this is doing a lot better than it used to. Hey, Curtis Horn, how are you? All right, so
Pod had a
oh yeah,
very deep exposure of the Pleiades and the dust clouds a day or two ago, I think.
oh wow. That's pretty cool. All right, let's see here. We're going to let this keep going for a minute. And now, okay. Well, so there's the Pleiades. And what's interesting is if we go look at the view from our 3D program here, all right, you'll see that the clouds of stars, now we've moved around it quite a bit, but if you keep moving back the other way, it'll eventually line up to what it's supposed to be, which is anyone's guess, but the four primary stars are these guys right here. But that said, if we could always go back to our Earth and then come at it again, which we'll do just for fun. All right. By the way, if you want this program, guess what? It's free. It's called Space Engine, and you can go do whatever you like with it. So I would say give it a shot. So now we're going to go back to Earth, which is in that crosshair. We're going to leave the Pleiades behind. There they go. See that? And then here we are. And now if we turn around and actually head back there, I'll do it a different way so we can actually study it a little better. All right. There we go. So now let's get out of here and let's head there. Now, obviously, with the bright sun, stars get washed out, just like in real life. So we're going to go forward here. And get my Pleiades back. There we go. All right, so now we'll move to the Pleiades, just like we're doing now in the telescope. You can see our rate of speed is right here, 42 AU per second squared. But now we're going to go a few light years at a time. Now we're going 5.38 light years per second. And as we approach, it's just so pretty.
There goes Aldebaran.
Yep.
There goes the high 80s.
That's right.
Yeah, here comes the Pleiades.
That's right.
Pretty cool.
Parlor tricks.
Yeah.
So, what's neat is you can see the stars, right? Very obviously. And this is Alcyone here. Okay, we've got Pleione and Atlas right there. We've got Merope and Electra and Maya and Taygeta. It's just beautiful how this represents these. But now, as we get closer, notice that we lose all semblance of what it is because it's not in the same 3 space to us. Okay? And so when we actually look at this from a different perspective, like to the side, which would correspond to a few light years away from the Earth, it looks all different. So this is the view of the Pleiades that someone has from a comparable distance. Well, right now we're actually we're actually 58 light years from these stars right now, and now we are 32. All right, so this is it's a special setting that you can set for, as you can see up there. Okay, it's 0.34 light years per second, and so you go a third of a light year per second, you don't see anything. 1.35 light years per second, 1.7, and only after you get up to several light years per second do you start to see any motion start to happen. So it's actually pretty interesting how this works. Whee!
There's a music video by a group called Explosions in the Sky.
Okay.
The name of the song is Last Known Surroundings.
Okay.
And this reminds me of it because, I mean, when you turned the Pleiades, you might see something completely different in it now.
Yeah.
And at one point in the video, it's sort of a 2001 Space Odyssey kind of animation.
Gotcha.
But they're flying through space, and they see groups of stars, like clusters like this, and constellations, what you would have to interpret as constellations, and they actually make all new constellations out of them.
Yeah, that's cool.
The imagination being what it is.
Mm-hmm. It's
really interesting. It's a cool video too.
Yeah.
You want to turn it up loud and go full screen.
Oh, that sounds like a lot of fun. Now, the thing with this particular program is it doesn't have every single nebula in it, but you can go racing through the galaxy, and I think that's pretty cool. Okay, Michael Hedrick says, Mark, can you please show to the side left and right 10 light years of the Pleiades? Well, I mean, I could turn to the left. All right, there's Magellanic clouds down there. Large Magellanic and small Magellanic clouds. Center of the galaxy, right there. And this is, again, it's not a cloudy night stream, because we are right now integrating on the Pleiades right now. So if we actually go back to our screen, right, we're at 12 images that we stacked here. And I'm going to color correct again. There we go. Look at all that dust. So that actually looks pretty good. It looks just like I would expect it to look. Beautiful. This dust is so full-bodied, even with light clouds. That's pretty cool. I'm amazed at how well that looks. You know, not bad. Hello, Cindy Murphy and Jane. I didn't see you earlier, Jane. I don't think. Rock is with us. Rockstar, what's going on? You know, Jane likes the parlor tricks. That's good, Jane. Jane's been here. She's actually she was here for our Mars party and donated a big rock that I painted red, reddish orange, to look like a Martian rock down at the bottom of our long driveway, so people knew where to turn.
Mm.
It's cool. Yeah.
I held a comet party for Halley's Comet.
Oh, did you?
Back in early spring of '86 or late winter.
Okay.
And it was up in the mountains, and I made a series of signs showing people where to turn. And the sign was just it was like cardboard. It was a drawing of a comet with an arrow, and I had people coming in from off the main highway, miles and miles away, following the signs, wanting to see the comet. It was great.
Oh, that's funny. That'd be a perfect thing.
Mm.
Just so everybody understands, these stars are literally just a few of the 1,000 stars that are part of the Pleiades. Probably a lot of the stars you see here, a lot of the somewhat brighter stars, are all part of the Pleiades cluster and moving through space with them. And these are hot blue B-type stars, right? We have O, B, A, F, G, K, M. O is the hottest and bluest. B are blue, but not quite as bad as the O's. Not quite as hot. And then you have the A stars. And starting with A stars, that's the point at which we think you can have planets, is with A stars and forward. Because A stars, besides having these broad hydrogen lines, which I can explain what that's about later, A stars have a temperature profile that would be conducive to forming planets, you know, stability of the star and so forth. And as you head down toward the cooler stars, the coolest stars are the M stars. So O, B, A, F, G, we're G, K, and M. Okay, getting progressively more red. The reddest stars, the coolest temperature stars, there's more of them than any other kind. And you might say, wow, and there's more planets around those types of stars than any other type of star. So you'd say, wow, there's got to be lots of life out there. We could be right about that. You could be right about that. However, M stars are also known as flare stars. They give off a lot of ultraviolet energy, especially in their younger years and as they age. So it may not be the perfect location, but if there's any chance that a civilization can form, it'll probably form. And the reason we say that is because our star is not the easiest star to be around. In fact, our star's been trying to kill us since we evolved. You know, skin cancer comes from our star. You know, other forms of cancer come from our star and mutations in our DNA caused by the ultraviolet radiation. So it's not the best planet for human life. How about that? We're not what's called a super habitable planet. Okay, we're habitable, but we're not super habitable. You know, so I think that's pretty cool.
Maybe we just need fur coats again.
Well, we used to have them, didn't we? Yeah, yeah. But I think it makes sense that we have turned out exactly as we have. You know, I'm going to save this just like this. All right.
Michael Hedrick said a little while ago what he meant when he wanted to see like.
Oh yeah. What do you mean?
Why I think you had been doing it yourself. You were sort of like you were off a little ways from the cluster, and then you were rotating the cluster left or right.
Oh, I see.
Pretty much what you were doing earlier, I think.
Okay. All right. Well, I mean, we could just do that again. Here's the Pleiades right here, and what we can do is let's see. We can come a little bit closer and head left a little bit, and then basically this is what we do. We just keep looking at it. So this is going around the Pleiades, all 1,000 stars that are part of the Pleiades. Now, the dust continues all the way to our solar system from what we're seeing now. And the Pleiades, being only a few hundred light years away, are stars that could very well be passing through the dust that we may have been born into.
They talked about that in that APOD. That is this just recently discovered?
Yeah,
this is like the whole. I mean, we're sort of connected to that through that dust cloud spanning.
Seems we are
local space.
Mm-hmm.
Fascinating.
Yeah, it's really cool.
I had seen some other speculation in maybe the last year or two that some question of whether we were actually in a nebulous area. And or if there was one nearby.
Yeah.
I guess maybe this is the answer to that. In the dust cloud.
I think that's probably true. I think that we're probably part of this dust cloud that the Pleiades is in. Yep. Hey, C. Ramos is with us. How you doing? Nice of you to come see us. I believe you're in Chile, aren't you? Yeah. Yeah, so Daisy and Zoe, hi, how are you? I thought our son loved us. Oh, that's a great comment. Well, I guess it's true, but I think it's more that we love the sun, and it's not necessarily true that it loves us. Again, the universe is trying to kill us every which way we go. Hey, Magical, what's going on? Magical, I tell you. Behold. Yeah. So this is the Pleiades here. Now, coming back to our screen, okay, this is also the Pleiades as seen from the telescope live right now. So we're actually, like I said, it's the new feature we've integrated into this. So whenever we go to something, if it's possible, we're going to go check it out, move around it. And so it's pretty cool to do that. And we got 36 frames saved here, so I'm going to save it again.
Have I got one for you?
I want to see it. Tell me.
I mentioned this recently. Well, no, I mentioned it in a Skype chat that I recently learned the name of Iota Orionis.
Oh, really?
Yeah. Well, come on, let me out here.
Is it?
Trying to change screens.
It's Skytour Livestream, isn't it?
I'm sorry?
It's Skytour Livestream, isn't it?
What?
The name. I know it's not. Come on, I'm kidding. I'm pulling your leg.
Okay. It's the bright star just below the Orion Nebula.
All right. Well, let's see. Let's go to Orion right now. And I'd actually like to. All right, let's do that. Let's go to Iota. Let's see if we can do it. We can see Iota right now. Actually, this would be perfect.
I was wondering if it'd be too early for you.
No, I think we're good now. First things first. Let me just do a check here. Yeah, we should be okay. That was
you see the nebula there, and then the bright star just below the nebula, south.
Yeah, right here.
Yeah, Hatysa is the name of the star. And I never knew that before.
Okay, let's go see Hatysa.
And it's a great big, it's a spectroscopic multiple star.
Okay.
And I think some of it's optical multiple star too.
Okay.
Maybe if you can get to Orion Nebula in
We'll see it.
Space Engine, you can do the same 3D thing,
Yeah.
like look at the nebula from Hatysa and vice versa.
Well, actually, we can actually go look at the Trapezium, which is what I'm going to do. I'm gonna show folks the Trapezium, which is really cool. And then you turn the Trapezium around and see the stars that are causing this to illuminate. But there's Hatysa right there, now that says the lost jewel of Orion. It's a star cluster, and I guess Hatysa's in the star cluster. All right, well, that's cool. So let's go there. Why don't we go there and check it out? All right, so coming here, we're going to actually back out a little bit now. Right now, back out some. And we're going to say, go there. And you'll watch the telescope move now. It's going to move, zipping over. There it goes. And
when you see the belt of Orion, Alnitak, Alnilam, and Mintaka, well, that's around Orion's waist. And then when you look toward the nebula, it looks like several stars or fuzzy stars in a row hanging off of Orion's belt. And that is his sword. The Orion Nebula is the middle star in the sword, and Hatysa is the bottom star in the sword.
And there is his belt, and there is the sword. And if we actually just get rid of all the stuff for now, you can actually see Orion's belt and his sword. There's the sword. You can see it in his belt right there. Yep. The ancients had quite the imagination. So you're saying this is Hatysa right here. Or is it? Yeah, this is going to be. This is almost straight down from the Running Man, so this has got to be Hatysa. Let's go back to Stellarium and make sure we find it. Actually, I'm gonna do this. I'm gonna come over here, and I'm gonna try and do a find on Hatysa and see if it's known by the name. Sometimes they are, and sometimes they're not. Okay.
Hatysa, I believe.
Yeah, I read it up. It's actually it's labeled here. So let's bring that up again. All right. Come on. All right, there's a little delay right now. Okay, now we're good. Yeah, right there. See Hatysa. Neral Saif. I have to correct something I was telling you all. When I told you how when we actually go in 3D to Orion, I was saying that Betelgeuse is closest, but it's not. Bellatrix is actually closer to us than Betelgeuse. So I made a mistake. All right, so let's go here, and let's see what changes here. Not all that much. Because I thought this was Hatysa right here. And I think we're looking at Hatysa. Yeah, that's Hatysa.
I thought Orion showed, or I thought Stellarium showed. Can we zoom in a little bit? 'Cause it looks like it shows a star to Hatysa's right, and on your image, it looked like you were pointing at a star with another star on its left. Or is my scale off?
I know what we have to do. We have to first make sure we're comparing apples to apples by showing our field of view. There it is. So that's our field of view. Hey, Sean, thanks, man. Thank you so much. All right, so it'll be from Hatysa down here. Okay, there's a star to, yeah, it's just right to the right. Let's see what's going on here. I'm wondering. See what that is? You know what that is? That is a geosynchronous satellite right there. And you'll say, well, wait, why is it moving? Because it stays over the same spot on Earth. It's the stars that are moving. Now watch, I'm going to stop tracking. I'll turn off the tracking and watch all the stars start to move. Oh no, wait, that might stay there. That might not stay there. Yeah, that's not geosynchronous. It'd be going east-west. My mistake. Duh. All right. But that's about the amount they move. Okay. We should have three
Michael
stars
has a
at the
question.
top.
Let me answer.
Yeah, read it first. Make sure.
How many stars had names in the ancient world? Or did they name mostly constellations? Michael, they had a lot of time on their hands during night watch back in the ancient world, you know, that they named all sorts of stuff. A lot of stars had names. The star names we know nowadays are mostly Arabic, where when it was the Dark Ages in Europe, the Arab world was still doing their observations and making notes, and the Arabs named most of the bright stars we know today, and they named a lot of them. Constellations go farther back. They do indeed go back to the ancient world. Some like Scorpius in the summer sky. Those are some of the oldest things ever. Those are many thousands of years old. Nowadays, stars are named by the International Astronomical Union, but they mostly go with the classic Arabic names. I'm sure you go far enough back, you know, like caveman names, they probably had their own names for stars.
Yep.
Again, you know, nights were long during the night watch, and they tried to keep themselves awake by naming stuff.
Yeah, I bet. Hey, Goblin, how you doing? Cosmic Ray. All right, so this is Hatysa right here, Daryl, and if you watch this, see 1, 2, 3, 4. See that little ring of stars around it? So we'll come back here, and 1, 2, 3. There's Hatysa. 1, 2, 3, 4. So we have 4 stars right here that are circling it. So there we go.
Cool.
So let's go and let's find out. Let's check in now. First of all, I'd like to take in the exposure of this southern area just below here. So we're gonna start a nice exposure here. Let's go 25 seconds and go into our stack. Start stacking after we clear the previous one. Yeah, beautiful. So we'll clear the Pleiades, which are already up on the server. And now,
yes, you were right. Hatysa is a member of the open cluster NGC 1980.
good.
Uh,
So let's do this. All right, and let's see if Hatysa is known by its name in here. It may not. Is it NGC 1980?
yes,
All right, let's see if NGC 1980 is in here.
the cluster is 1980.
There it is, right there. So we say okay, and of course it's going to be over there. So we're not near Earth right now, so unfortunately we need to go back to Earth in order to set the view correctly. So we're looking at it from how it looks to Earth. So that's the only thing we're going to do is go back to Earth each time, which is okay. It's going to be fast. Zoom, see? And now let's go back into here and let's go into NGC. Let me see if Hatysa is known by that name. Hello. Okay, it's not known as Hatysa. So it is known as NGC 1980 though. All right. So we say okay. And now when we go there, we're going to go there as if we're going from Earth. There's Orion, there's Betelgeuse. Here comes Bellatrix, there goes Betelgeuse. There goes the Orion Nebula. And here is the cluster NGC 1980. There you go. Not bad. Right? And we can go around this too. And Hatysa is a member of this group. Now as we spin around, okay, what you'll find and you'll see is that we also have the Orion Nebula. Notice the dust of the galaxy. Yeah, there's the Orion Nebula right there. I imagine that's part of Barnard's Loop right there. So, very nice. You can see that the nebulas don't, this is the flame. The nebulas don't actually look like they do because we've now moved to one side. Hey, Judy M. Space engine, cosmic ray. Yeah, so there's that. That's the cluster we're looking at right here. If we come back to our view right here.
So are you looking through the cluster there?
Yes, we're looking. I turned around and went backwards through it.
Okay.
All right, what I'm going to do now is get back to our view here. And all right, so there's the cluster right there that we're circling around. Now, what's interesting is this program recognizes that stars are just points of light. They're big and bloated here because the photographic sensor makes them big and bloated. But they're not big and bloated when you look at it in reality. In reality, it would actually look just like this. You would see these stars. They would just be slightly brighter. And, you know, you'd see that they're brighter, but they're just pinpoints. So this is an accurate rendering physics-wise of what you might actually see, as opposed to this. Okay, this is not actually accurate, but it's the best we have, right? So that is Hatysa right there, and it's part of NGC 1980. And now, if we look down here, you'll see that we have the beginnings of some of the dark nebula down here that you can start to see. Again, we're looking through light clouds, and I will show you that. Okay, let's pardon the bird poop on our black and white 3D camera here that we have, our 3D, AllSky. But let's just do a, let me set the settings here. And for the AllSky, this one's going away. We're getting rid of this AllSky, and we're going to put the new one in place. The new one is just unbelievable. All right, this one's going to be 12 seconds. So 12,000 milliseconds. Save changes and go get a single shot. I suspect we're going to see a cluster of clouds off to the west side here. If they're not already over us, we're going to find out. Yeah, there they are. But not bad. Overhead, we're looking here. There's Orion. There's Betelgeuse, Bellatrix. You see Rigel here, and you see Safe here. There's the Orion Nebula complex right there that we're just below. There's Al-Nataka, Melamed, Mintaka. There's the upper stars just above, in between Betelgeuse and Bellatrix. We have these stars here, Mesa, and it's there's a large nebula up here, which, by the way, we'll be able to see that with this new camera because the color is just stunning, and it's much more sensitive than this camera. So that said, here's the winter Milky Way right there. You can clearly see that. You can see our dark nebula, otherwise known as bird poop. I've come up with a way to keep birds off of our new camera. It's a proximity sensor that detects when a bird comes in, and it raises a flap, and it's like, it scares the birds away. Kind of like a little active scarecrow. So that'll have to be taken apart. I have to disengage it, though, when I go to do any work on it, because otherwise it keeps slapping me. Yeah, so I'll probably integrate that. One of the things I also did was I actually made it. The problem is when you got an AllSky camera, right? Well, you got to power the AllSky camera somehow. And let me actually show it to you. So we're integrating right now. So while this
That's a cool picture all by itself.
It is. So I'll be right back. I'm going to show you the camera and talk to you a little bit about how it's going to work.
When we see Hatysa there,
Let me just.
that's
put
an
my
optical
ears back
triple
in.
star. Plus, it's a spectroscopic binary. Two stars are so close to it that we can't separate them visually.
Okay. All right, so what I'm going to do right now is I'm just going to abscond with the view for a minute and just show you the background here and enlarge this for just a minute. Hi, guys. Haha. So, this is the camera that I made, all right? Now, it's in a watertight case, and it has only one cord going in, and that's an Ethernet cable. And what I'm doing is I figured out how to get, and I learned this by studying the stuff that people are telling me about this. Your Ethernet cable usually just carries data. But what I'm doing is I'm actually carrying 48 volts over the Ethernet cable as well. And there's another unit back there that injects 48 volts into the Ethernet cable because my Ethernet doesn't do this. It's called power over Ethernet. So I put a power over Ethernet injector over there, and then inside this box is something called a PoE, or power over Ethernet splitter. And now the splitter takes the power out of the Ethernet cable. It delivers you an Ethernet cable just with data, which goes into the camera, all right, and takes care of all that. And then the power goes to the circuit called the Raspberry Pi. Two latches open this up. And then once it's open, you can see that you have the black box in there, which is the Raspberry Pi. This other little skinny one, that is the splitter. That blue cable is the cable to our ZWO camera up here, which is a ZWO. It's an ASI 678 MC. And I've got a couple holes in the top of the case there. You see the holes in the top. Well, obviously it's below the dome. What that is, and it's effective. It works. I already tried it. we had a snowstorm. I put this out in the snow. No water got in. It was totally watertight. However, there was snow in the dome. So those holes allow the heat built up in the circuit in here to come up through the holes, a very gentle heat, and it melts the snow in the dome. So it's an automatic clearing. Pretty cool. So I thought, why not try it? And it works great. Now I had siliconed this dome down to the plastic, and then I realized, but if I want to change the lens at some point, I'm going to have to just have a gasket. So I actually cut a rubber gasket, and I put it down, put it through, and this is now ready. I just have to, it's going to get screwed down to the SkyTour live stream end bars, the end supports there, and it'll probably sit on top and get screwed from above. This is like 1 or 2 screws. That's all it's going to need. It'll be perfect, you know. This is the south side, so this is going to be the part that's facing to the south, and it's going to be nice. So this took about 4 days to build once I had all the components, and it's beautiful. It does a gorgeous job.
Well done. That's pretty.
Yeah, it's a nice piece of engineering. It's a watertight case you can access with just 2 latches. I mean, come on. And the wire, it's called a gland. It's the thing that the wire comes out of the case with, and that's a waterproof gland. So by tightening that down, that you tighten down the outer ring, and it squeezes a rubber gasket around your cable and prevents anything from getting in. And it works very effectively. I'm very pleased. So that's one of 3 that I'm making. I'm making 2 more identical ones, and those are going to be for the other SkyTour West, which I'm going to go out and check the site out in the coming month. And then one is going to be for SkyTour East, which will be our temporary East Coast setup. So it's looking pretty good, you know. But that, I cannot wait. You should see that. Oh, it makes time lapses, which I think I've shown you, and it makes kiograms. So at a glance, you could see how the whole night went with clouds or stars, whatever. It's really, really cool, you know. Not bad. All right, let's see here.
Well done.
Oh, thanks, Daryl. Coming from you, that's a compliment, because you're actually probably the consummate engineer. Notice now that this star and NGC 1980 are sitting amid a whole bunch of beautiful dust. Look at this dust. Isn't this incredible? This is the part of the Orion Molecular Cloud Complex, the OMCC, and it's dark, cold dust. Now, we're going to take a journey into the heart of this nebula here in just a minute. So we've got 25 shots. We're going to save it here. Of course, I'm saving it under the Pleiades one, so that's wrong. I'm going to rename it. Do that right now. M42 region. All right. Yes. So we'll save it again, and we probably, if it tells us it's an error, it means it's copied it over. Yeah, I gotcha. Yeah. It's a threat. It's not true. Okay, it was saved.
I have to remember that.
Huh? Hatysa.
I have to remember that. Hatysa. Yeah. Maybe be interesting to see if you or Izabela might, do a process on the pic. That looks really cool.
Yeah.
That's like that has that Gustave Doré kind of biblical up in the clouds look to it.
It does, doesn't it?
Yeah.
That's a good analogy. All right.
Slick.
Yeah, so here's what we're going to do now. We're going to, first of all, since we have some pretty good weather in Orion right now, I'm going to, because those clouds are heading for us, I know they are. What I'm going to do now is I'm just going to move us a little bit north. So I'm going to go back to our 1 second shot here. This will be our finder view. And we're going to go up north a little bit, and I'm going to show you the next item that I want to show you, and then do a 3D view of it from our wonderful program here. So as we get now to the nebula being centered, the Orion Nebula, right, this is what's really pretty. Let me just make sure that we're all focused and everything, because once it gets in here, I got to make sure we're focused.
Nice short exposure like that. I can see Bill Murray eating the baby Ruth.
One of these days, you're going to have to show me what you mean by that, because I can't see it. First of all,
Your pointer's on the baby Ruth right now.
this is the baby Ruth.
And his mouth, yes.
This is the mouth.
And that's his nose just above the baby Ruth.
Ay, ay, ay. I don't doubt you.
And his eyes. Eye, that is. Like you're
Okay.
seeing him from the left.
All right.
His face is in profile.
All right. Okay, I'm going to do a focus here. Daryl, I don't know what you're talking about. I can't see a thing. It's fine. Fantasy saw it. Look at that. He says, hey. He says, yes. Hey, dude, what's happened? I'm running through the focus setup right now, guys. So after this focuses, I will lock it in and we'll do the exposure. While it's focusing, why don't we go over to our other setup here, and I'm going to go to Earth again because I want to, well, that's not Earth, that's a star. I'm going to go to Earth again just to reset and get us going. Look at the plane of the galaxy there. That's beautiful. Okay, now from here, we're going to go to Messier 42, M42. Okay, so here we go. Okay, well, you can kind of see the shape of M42 right there. All right, and dead center in there is the Trapezium. These are the stars that are causing this whole thing to illuminate and be illuminated. So we're going to head into there and just go exploring. There's lots of dark nebula in here. Look at that. There's the 4 stars of the Trapezium. See them? As we get closer, the 3-dimensional world takes over and you lose the orientation really, really quickly. But there we go. Those are the 4 stars. Now, some of them are B stars and some of them are O stars. And so it's actually a pretty good mix. All right, let's go a little closer. Let's dive into the heart of the nebula a little bit. You can see dark nebula going by us here. Okay, you notice the Trapezium is not just 4 stars. There's more stars in here. All right, which is kind of interesting. And as we move around, you'll see that they can have their light extinguished by the dark nebula just like any other. It's a little harder, but they can also have that happen. But they're also very, very bright stars. Notice you don't see any of the 4 stars anymore the same way we see them. Look at that. Now,
I've seen 7 stars now.
yeah, I'd be remiss if we didn't also visit a globular cluster tonight, because I know that Izabela had asked for us to go through a globular cluster. And I'm going to do that for her because I don't think she's here right now, but it's okay. Here we go.
I think I already knew this, but so some of the Trapezium stars are actually multiple stars.
Yes.
Yeah. a lot of multiple star systems in Orion.
Yeah, there really are. So that's the visit to the Trapezium. And now, what we want to do is go view what that looks like here. So I think that by now our focusing has been completed, and I can set it to go. And oh, not quite. It's almost done. We'll see a line. There it is. There's a line I was just about to say we're going to get. And now we'll go to best focus here. If it would pay attention to me, I would do that. There we go. Okay. There we are. All right. All right, so there we are. We're all focused up. Now, let's take a look at those 4 stars. Let's drop these down. And as you notice, now, this is what it looks like to us. Here is the Orion Nebula, okay, that we see. The trapezium is so bright that it's actually illuminating more gas than the stars and making it hard for you to see the stars. But if we actually cut through that and reduce the exposure, now we can actually zoom in on this and see the stars that we can see from here. 1, 2, 3, 4, and there's more. Now that you know that, all right? So this is what it looks like in 2 dimensions to us, because it's a projection on the sky. But they are, as Cosmic Ray points out, they are really truly close together, as we saw in the 3D space view, right? We rotated around them and they stayed in a little tiny group together because they were formed all at the same time in this location, right? So really cool. So now let's back out a little bit. And now let's do the same thing we did earlier. Let's do a 25-second exposure here again, now that you've seen it in 3D. Okay, and go into our live stack. You can see our yellow bar over there showing the progress. Go into the live stack and we'll see the previous shot, unless I cleared it. I don't think I did. There's that previous shot. Look at that. It's soft focus too, Daryl. I think I'm gonna have to do it again.
Yeah.
But I will. No biggie. All right.
Daisy and Zoe want you to do that to the Flame Nebula.
I bet they do. All right, we'll do that.
You've created a monster, Mark.
I love it. This is what it's all about. You know, it's very important for people to understand that they're not just projections, that things are farther away than they appear. And that's why it's so important for us to do exactly these things. So I'm okay with it. And what's nice is we are going and doing the real view and the rendering view, the 3D view. No one's doing this. There's no one doing this out there. Okay, so here is the Orion Nebula now with all this beautiful dust in it, all right? And let's see where it wants to process. It's going to probably, right, that's what I thought. So you can see what it's doing here. It's really stunning. Okay, here's the nebula. Okay, there's Hatysa down there. As you know, these lines that we're seeing, these are geosynchronous satellites going east-west, west-east, I mean. And so it appears, you know, as we're rotating out from them, they're staying over the same spot. Okay. Let's go here. This is our middle line. Let's bring that in to start to bring out some more details in the dust. This mid-level view. It's very nice. Yeah, now you see how much this is. This right here, this stuff here, this greenish blue, that's oxygen that's been doubly ionized. The oxygen atom lost 2 electrons briefly, and they come back. And they did that because of the ultraviolet energy from the stars in the middle here, ionizing those atoms momentarily. Ionization is when those outer electrons in the outer shells, the valence electrons, are pumped up by absorbing energy, ultraviolet energy from in here by these bright stars. And that higher energy makes them go into higher orbits effectively until finally they're free of the atom. And then the atom becomes positively charged. In this case, oxygen has a +2 charge. When all the electrons are in an atom that belong there, then all the protons at +1 are balanced by all the electrons at -1. Okay? And so you have a 0 net charge. But when you have an ion, the nucleus is a positive charge because one of the electrons with the -1 charge is missing. In the oxygen, we have 2 electrons that are missing, so it's a +2 nucleus, a charge of +2 in the nucleus. So that's how ionization works. And ultraviolet energy is the conduit through which electrons can travel through these different energy states within the atoms. So back over in our program here, we're actually looking at the trapezium, right? And in the trapezium here, we are, let's do this. Let's center you. Okay. Let me go forward here. See, now we're right in the thick of things here. That's pretty cool. Again, you see slightly brighter and a slightly less bright dots because stars are literally only points of light. So in reality, if we saw stars only the way they were, it'd be a very boring universe to us when we take pictures because they would all be approximately the same little tiny dots. But that would be a reality because the universe isn't as we see it when we look here. Okay, this is artificial because these stars here, okay, these are actually bright only because the sensor is picking up more light because they're brighter, and so the light spills out into the next adjoining bucket. It's a set of square buckets, so you keep filling the square buckets with all this extra light, and the star image gets bloated and looks bigger. Yeah. Cosmic Ray says when you look in the eyepiece, you can see the green nebula around the trapezium, and he's right because I have seen that. It looks very green. Jessica S., how are you? Nice to see you. Thank you for coming in. And by the way, Calabos is here. Calabos and Tiffany are our 2 partners, wonderful people that have joined us. They're official volunteers for STLS, Skyter Livestream. And they also have entrusted Skyter Livestream to be their conduit for giving away telescope equipment. And we're honored and humbled by it. And so far, we've given away 3 items, 1 telescope and 2 binoculars, with many more to come. And if you want to know who won the last ones, all you have to do is go up here to skyterlive.org. And if you scroll down, you'll actually see the winner's circle. All right. And then we'll put every future winner will be put up there as well. So that's pretty cool. And that's Calabos and Tiffany. Cosmic Ray's always bad fantasy. He's always bad. That's why he always gets, he's always getting timed out. I'm kidding. He hasn't lately. Look at this beautiful, beautiful, beautiful nebula here. This is stunning up here. I'm going to add a little detail to this that I didn't before. Ready? Let's add it. Watch this. Check this out. You see how sharp that is now? Look how much sharper that is. You can see even more detail in here. We can now zoom in, Daryl. Oh, look at that. Move it down.
That's M43.
M43, that's right, yep. Look at the details in M43. Just beautiful. Yeah, wow. Yep. Nice indeed. And as you can see, the trapezium has just blown the center of the nebula out of the water. Our eyes don't see it this way, but the cameras do. And if we were to reduce this as far over as we can go, we still would have it blown out of the water. Watch this. See that? Still blown out of the water. Let's bring it all the way over. Now we're down in the weeds. Still blown out of the water. All right. So that's pretty much how this works, Cameras will cause the image to bloat, and our tool that we're using here, the Space Engine view, actually shows us the reality of how it would look. Pretty cool. John P. Adventures, what's going on, man? Nice to have you with us. Nice to have you with us. If you guys are of a mind, any of the new ones, the new folks, you might want to consider supporting us with our Patreon. Several people in the chat support us with the Patreon. We have a number of levels, for everybody. And I would just we would really appreciate this, because it allows us to do builds like that AllSky camera. That AllSky camera is a product of your support. We're actually going to be putting that out at the Arizona Observatory, and then we're going to put the two others at the second Arizona site, and then one out here at our temporary Connecticut site. James Hyatt, thank you. Speaking of Patreon supporters, I'm glad you think it's worth it, because I'm not getting paid for this. I don't care about that. I just want to see everybody learn some astronomy. That's why we're doing the 3D stuff now and showing you this stuff in 3D, so you can see the three-dimensionality of the universe. MPG, how you doing?
I have a question.
Sure.
You mentioning the AllSky camera again reminded me. Is that basically a 180-degree fisheye, or do you know how many degrees the field is?
I do. It's 170. But the problem is I'm losing a little bit of the top and bottom. It's the cutoff is strange. I don't know why it's doing it. I think I know, because the spherical field can't all fit on the sensor. So I have to get another lens for it. But you see really quite enough. You really see quite enough. And it's really nice, because it's meant to look at the weather. It's not the nice thing. I got to tell you though, I have to say, there's a website version that I'm going to have up, and when you go in, you click on it. There's a little menu on the side you can click on. As you click on it, there's one that looks like Cassiopeia. You click on that, all the constellations come up, identifying where you were looking and what everything is, and you see the Messier objects listed. And when you hover your mouse over them, guess what happens? It takes you to see the image of what this thing actually is. So it's actually really cool. Hey, Lubo. Lubo says it fits the ASI 290 mini. Okay. Yeah, I'm using the 678, so I need a different lens to make the entire image field fit spherically. You know. But the nice thing is, Orion went by the other night, and I had it outside before snow came, and I could literally zoom in and see the Orion Nebula on the AllSky cam, and zoom all the way out to see 170 degrees of sky. Really quite nice. Okay, we're gonna save this now. Save exactly as seen. Not bad. Okay, so now what we'll do, now that we've done this, is we're going to go back to our finder, our sensitive finder here.
I have a request before you leave, Orion.
Yeah.
Okay, seeing that right there, if you don't see Bill Murray eating a baby Ruth, well, look at where the... no, I won't say that. You're familiar with Barney, the alcoholic on The Simpsons?
Oh, yeah, Homer.
Yeah, do you see Barney? He's you know how when he belches, his lips flap?
Well, I would say this is his mouth, if that was true.
Well, a little higher up is his mouth.
This is his mouth?
Where it's dark, the dark area, that's his mouth. And his lips are flapping like he's belching. You see that? And that's his nose right where your pointer is?
Right there.
Yeah. It's like you're seeing him from the left. It's a profile.
Uh-huh.
I mean, he's got a...
Is this an eye?
Yes.
Yeah, I don't see that.
That's an eye and his nose, and there's his mouth. He's belching.
Yeah, and he looks like he's throwing up.
Well, you said it, not me. But, anyway, so you don't see Bill Murray. Maybe you see belching Barney.
I can kind of see what you're talking about, but why Bill Murray and not like, some other actor?
It was just the first thing that came to mind.
It actually looks like Bill Murray to you?
It looks like a baby Ruth.
Okay. All right, Lubo says, any tips for free software converting fits to color time-lapse? I had no luck. As a matter of fact, Lubo, why, yes, because I just showed folks the AllSky cam I have here, and the software here that I use is from a GitHub for a Raspberry Pi by Thomas Jacquin. If you look up GitHub AllSky Cam, you'll find Thomas Jacquin's Jacquin, I believe. And what that'll do for you is that'll give you software that will make a time lapse at the end of the night in color, and it will convert the FITS files it makes to an MP4 time lapse, and then it makes a keogram, makes star trails. And plus it's just beautiful. You see star trails too. I just love it. Making star trails and keograms from inside is really not all that good. But when I had it outside, wow, is that something. That's just incredible. So, but Lubo, that's what you want to use. You want to go, I think, use Thomas Jacquin's software, because that will do all your time lapses for you with an AllSky camera. All right, and it's free. And it's free. Do you have the link? Yes, it is for the PC, Lubo. In fact, and it's also as I said, free, and it's made for Linux. Thank you very much, Daryl. It's made for Linux, and it's for Raspberry Pi. Now, our camera, I've never used a Raspberry Pi before. I kind of knew a little Linux, Lubo, so I was able to do it with that. And I'm telling you, it works great. It works really great. So that's what you want to do, and it'll convert and make your time lapses. Actually, there's the name of the program in the directory is called FFmpeg, and if you run that with the right arguments, you can take all of your files and turn them into time lapses. But you don't have to do any of that because it'll do it for you. So let me know how you make out with that. Okay, I'm going to take us up a little north now. Did you have anything else for me to mention, Daryl, or are you all set?
Go ahead.
Okay.
Daisy and Zoe would like to see the flame and to do it in Space Engine.
Okay. I figured that they would, and from what they said before, yeah. So we'll do it. Right now, I'm going to go here. We'll do the Running Man complex, and then we'll go over there and do the flame. Let's find out if this
Maybe you should do the horseshoe also, or the horsehead.
Horsehead? Oh yeah, that's I know that's there. Okay. All right, so we're good here. We're searching for a guide star. See the word searching right there. All right, we're guiding. So I'm now gonna make this a 25-second shot. 25 seconds. And off we go. And we'll live stack. We'll see the last Orion shot. God, that's beautiful. And what we're doing now is we're just coming in right up above this. All right, so we'll clear this. It almost seems sinful to me to just clear that, right? Because it's so beautiful. And so when we go up to the Running Man Nebula, which is where we are now, okay, all right, the Running Man is NGC 1977, and this is it. All right, so there's NGC 1977. We'll color correct it, and we will process it a little bit just to get it. And we already start to see this beautiful dust. Let's go over and check our system, make sure that we have enough sky to do this with, because we're literally right there in the sky, and those are the clouds that may be coming toward us. We're going to find out. Okay, 2 seconds. All right, we are clearing the clouds better than I thought. Excellent. All right, good. So we can continue this. Look at that. Nice, nice, nice. There's still light clouds up there. That's why this looks kind of grayish and a little red cast here and there.
Lubo asks if you're going to show supernova too. Maybe if it doesn't get too late for the crab in Taurus, you could do that and pivot around on it in Space Engine.
I think that it's there, yeah.
I bet it's in there.
Yeah.
That's a showcase object.
It is, yeah. Well, let's do, this is NGC 1977, and we'll see if it's, we're going to see if it's actually in Space Engine as well. We'll just let a few more frames come in here. And once we get a few more frames in here, we'll be able to check it out. It's really pretty.
Running Man looks like he's wearing a dress.
That's kind of strange, but okay. I will have to allow you to, well, I don't know. I'll have to allow that for you. I don't know whether it's true or not. NGC 1977. Okay, hold on.
Ronald's here.
Hey, Ronald, how you doing? Nice to see you, Ronald.
Django's here.
Mr. Django.
Mr. Django.
You got it. Okay. Interesting.
Oh, Lugo said he's referring to a particular supernova happening right now in NGC 4216, 4216.
Look it up, see if we can see it. Will you do that?
Yeah, give me a sec.
Okay. All right, so since we're looking at this, the Running Man being built, let's go see what it looks like in real life. Okay, so here's the Orion Nebula over here. All right, and here on the left, and here is the Running Man Nebula here. So let's move forward a little bit. Okay, 1 second. There we go. There's the Orion Nebula, and now we'll close in. So now you can see, let's see if we just do this. Now you see it like you're used to seeing it. See that? Right? But interestingly, as we move forward, here's something when we spin it in 3 space here. Okay, it looks a little weird, doesn't it? Right, so let's do this. Let me actually spin us around. Now, not all the dark nebulas in here or anything, but you can see right from here, you can see that it looks like the Running Man is further back, further away from us, because we're to the left out there. But that's pretty cool. Again, it's just our view. So you remember, Daryl, when I told you, when we look at the Running Man and we see those beautiful brown clouds,
Yeah.
I thought that maybe those brown clouds were actually heading away from us and toward the Running Man. And that's kind of what this is, right? So here let me just bring us over here. So it's kind of like this. So there is the Orion Nebula, and there is the Running Man. Just like that. And so those dark clouds are heading here and moving through toward the Running Man Nebula there. Pretty cool.
Lubo supernova in NGC 4216. 4216 is in the Virgo cluster, and it's way too early for that here.
Yeah, we can't see it yet. Thank you, Lubo, though. That was a good thought. So here we are moving around the Running Man. Again, the stars are shown realistically, and so we see them as points. We don't see them as these blobs like we see on all of our photos. But from the same perspective that we're used to seeing it, okay, if we were on the other side looking at it, this is what it would look like right here. This is what it would look like to us. Interesting, huh? And so all around us are these nebulae. That looks like Barnard's Loop right there. But that's the 3 dimensions of it, so that's actually kind of cool. Neat. Very cool. So back in our view, you can see that we have been. You can see that we've been working on shots. We've got 12 of them right now. So you just got to see this in 3D, so you can see kind of what's going on there. All right, so let's
I think I missed something.
okay.
Did you have the Running Man up in Space Engine?
I did.
Oh, okay. I didn't realize my YouTube was. I have to go to YouTube to see Space Engine,
Yeah, you do. That's right.
and it wasn't live, so I didn't see it.
Okay. So there's Measure 43 down here. Right? And right there's a Running Man. And now, from what you saw, from what we showed, you saw that the Orion Nebula is here and the Running Man is back here, a little further away. So there's some three-dimensional distance between the two, and now you know that. So now it's almost like you can see that happening. You can almost see how this is further away. But the stars don't give it away. Yeah, I remember with the first time we were doing Sky Through live stream east, we actually couldn't tell all this detail. This detail was invisible to us. We're using a regular DSLR camera for the very first iteration of this, and now we're using dedicated astronomy cameras for everything, and so it really makes such a big difference. Look at this beautiful cloud up here. Look at that.
Oh.
Beautiful details up here. Oh, yes. Yeah. Beautiful clouds. Beautiful details.
Is Space Engine still on Running Man?
No, I've moved it off now.
Okay. Ray, I was busy looking up the supernova in 4216. I missed it. Oh well.
Well, it'll be there for you on the replay.
Yeah.
Okay.
He has a ponytail now too.
Who does?
The Running Man. He has a top knot, sort of like Genghis Khan or somebody.
This?
Yeah. Well, the dark thing's his head, and then he's got like a big.
This is his head?
No.
You said the dark
See the
thing.
Running Man?
Oh, so this here.
That's his head.
And there's the top knot.
Yeah.
Okay, I see what you mean. Mm-hmm. I have to say, we did purchase the commercial version of that space engine, and we added all the downloadable content. And I initially had literally almost 200 or 300 million stars in it. And even this computer, which is really high end, was having trouble with it. So I kind of backed off, and I think I only have 850,000 stars in here now. But still, it's okay. This is gorgeous. Look at this. Wow. All right. Well, we're going to save this because there's 28 shots. All right. And then we could go to the next object, which is going to be the Horsehead flame region. Beautiful. All right. So now let's do that. Let's head over there. All right, and to do that, we're going to go back to like a 25% view and head to our planetarium stellarium. And now we're going to head over to Alnitak. And there's the flame. So we're going to go right to the flame. And from there, we'll dive down to grab the Horsehead. Maybe we'll put it in the same view. So here we go. You watch the telescope move a little bit. There it goes. And you'll see the Flame Nebula come right in. Here it is. Here's Alnitak with its companion. Okay. So what we're going to do now is just drop it down a little bit. All right, and maybe a little bit more. The Horsehead should be right about there, so I want to just give us a little bit more so we can view it in the same view. You can already see
just,
the red
here
here.
to the west too.
Yeah, I mean, I'm gonna go that way with it.
Right.
Yeah. Let's see. Go down a little bit more. And you know why I'm doing that. And for the reason that's coming in on the lower right.
Sigma.
You got it. Sigma Orionis. A star that may have as many as 6 companions.
Maybe Sigma's in space engine.
It is, I think.
Might be interesting to fly around that.
Yeah, we'll go check it out.
Sextuple or more star system.
Yeah. All right, so this will put us at the flame. The flame actually goes higher, so we're going to stop here. Let our telescope capture a guide star. Meanwhile, I'll set it up. We're going to do 25 seconds. All right, we're guiding, and we're going. So I'm going to hop out of this mode. Okay, and go into our live stack. You can see our last shot of the Running Man. Look at that. Holy cow. Jeez, that's beautiful. That is so beautiful. And it's gone. Not really. It's been saved. All right. There we go. So the Flame Nebula goes up top here. Alnitak is here, and the Horsehead is there. Sigma Orionis is here. Sigma Orionis is responsible for illuminating this whole cloud. Alnitak, I believe, is in part responsible for causing the flame to illuminate. And I think there's some stars in the flame too that are in the dark nebula in there that may be doing some of the work. I'm not exactly sure.
I think there are, if I move correctly.
All right, so we're gonna pop this back a little bit. Oh yeah,
Sort of like North America and the Pelican nebulas are the big dark bars blocking the stars farther behind it. We can't see them, but we see their effect on the nebulosity around it.
Right. So down here is the Horsehead. We're capturing that. We already see the little tiny star in the top of the horse's crest right there. We'll let a few more images come in, and I think that's probably a good place to start. Let's see here. So what we're going to do is we're going to go to the flame. Although it's also known as the Maple Leaf Nebula, the Lips Nebula, the Burning Bush Nebula, the Ghost of Alnatok Nebula, and of course, by the names that we use, NGC 2024. Kind of funny. So let's go back here and watch this come in. Looking good, getting better and better. So Ronald, how you doing? Alright, so we're going to be approaching let's see here, let me check out our view. Yeah, that's really pretty. And we have a satellite going through ever so slowly. Looks like a somewhat it's rotating. So you see a little brighter, a little dimmer. It's making a dashed line.
Yep.
Yeah. All right. Beautiful details in there. Oh. I'm amazed at how beautiful this region is. This region. Oh, look, another one. Can't get away from them these days. Okay. And then we have these beautiful reflection nebulae. These are dark clouds of dust here. And the stars inside are, of course, sending out their light. And the dust inside is scattering the light that you see. Which is exactly why it looks this way. And we get in here and you can actually see a little bit more detail of what's happening in here. There's a beautiful stalk here. And you'll notice it has little tinges of red right there. And there's some more dark here. This is beautiful. This is a area that's been kind of carved out by this star with its stellar winds kind of pushing material away. So it's probably got a lot of stellar wind going on there. Yeah. This is there every night. Century in, century out. Now, as far as what it looks like, this is the Flame Nebula as seen in Space Engine. If we back out a little bit, you'll end up seeing some more details. Okay, like down there you see the Orion Nebula, and you see the Running Man Nebula down below. There's the Horsehead right there. So as we close in on the flame, all right, you're going to notice something about the flame and its relationship to the Horsehead. Well, look at that. It appears that the flame is actually in front of the Horsehead. We rotate around it. And right here we see Sigma Orionis. And of course now the Horsehead doesn't look like the Horsehead anymore to us. Going through some dark nebula, as you could tell. But circumventing the Flame Nebula here, let's push through it. And there's our Horsehead. Beautiful. And I'm going to guess this is Sigma Orionis right there. And it is. We're going to go to Sigma. and see how the Horsehead looks from the very thing that's causing it to be illuminated or backlit. So there we are. We just went by it. Okay. And there's Sigma. Not very impressive when you look at it this way. It looks better in our views when we look at it that way.
Yeah.
But that's, of course, because we're looking at it from the perspective of reality and not in the perspective of, a sensor. But if we look at what Sigma's illuminating this whole band here that we saw before, and our Horsehead Nebula, okay, is being illuminated by Sigma right here. That whole region. So you see, the three-dimensionality is very interesting to see, especially when you see it this way, because you come back in, right? If you come back in, you see it this way, and you say, oh, well, look, there's the flame, okay? There's the Horsehead, right? And you say, well, the flame is there, the Horsehead's there. This is closer to us than this. I have to confirm that stuff, though. All right, now I see Marianne's here. Hey, Marianne, how you doing? And Michael has a question. When is that 7-minute solar eclipse? 24 something. I don't know. I have to look that up. Fantasy, behave. It's the fuzz.
Michael, what causes a long eclipse?
No, he wants to know when it is.
When? Both, I think.
Okay.
When is that 7-minute eclipse? What causes long eclipse?
Okay.
A long eclipse is all a combination of how far away we are from the sun on Earth in our elliptical orbit around the sun, and how relatively far or close the moon is to the Earth at the same time. Like you've heard of supermoons, that's a perigee moon, when the moon is closest to Earth. If the moon is close to Earth at noon, it's somewhat closer and will cut out the sun for a longer amount of time. If the sun is in the far point of Earth's orbit around the sun, it's farther away, will appear a little smaller. So if you take that happens in summertime. So if you have ideally a summertime total lunar eclipse and the moon is at perigee at noon, you'll get a long duration eclipse.
That's a very good answer to that question.
I hope that makes sense.
I'm going to answer Lubo's question now. Lubo is asking if he should get a hyperstar for his Celestron 8 HD, or just get a Raza 8. Well, Lubo, let me just tell you this. If you get a Raza 8, that's all you'll ever be able to use as a Raza 8. If you get a Celestron 8 HD with a hyperstar, to change the hyperstar out and put your old secondary mirror back in is literally less than 5 minutes, because all the configurations stay the same. You're not going to lose collimation as long as you just follow the instructions. So do you want to have a telescope that can do both, or do you want a telescope that does only one thing? Now, yes, the Raza 8 will do that beautifully and do it great, but don't expect to get any high focal length shots. And if you're okay with that, then get a hyperstar. I'm sorry, don't get a hyperstar, get the Raza 8. If you want to be able to trade back and forth Like, say tonight you want to do a photograph with a close-up of the Horsehead Nebula. You'll take the hyperstar off, and you'll come out and use your Celestron 8 HD and grab some photos of the Horsehead Nebula. You can't do that with the Rosette 8. You're stuck. Let's zoom in on the Horsehead Nebula. Look at that. That star is just brilliant there. There's one in the nose. There's one in the main. Look at that. And there's even one inside here. That's nice. We're going to soften some of the noise here. So, Lubo, I hope that makes sense to you. Made sense to me. All right.
I can't get away from the satellites anymore.
No, you see him whipping through here. There's a lot more up there than there were when I was doing this and taking these pictures back when I was getting my degree in astronomy. We didn't have a lot of these satellites to worry about. Look at the detail in here. Look at that. This detail is really pretty. I'm going to just rename this and save this right now, because this is actually a good shot. Horsehead Flame Region. Okay. Save it immediately before anything. Well, I won't ever get any bad shots now because I'm using the full width half maximum filter, and as you can see, they've all come in okay. Interesting. It's actually quite high. Interesting how that's actually worked out okay. I'm going to bring this down.
I see a blue spot to the upper right.
Oh, yeah.
Of the Horsehead. Is
That's,
that real or is that an
no,
artifact?
That's an artifact from Alnatak.
Oh.
As is this. Yeah, because if we zoom out here, look at Alnatak. It's glaring into this.
Yeah.
And Sigma may be causing. I know Sigma's causing that one, but it might be causing a little of this. But I think Alnatak might be causing that in conjunction with that. I don't know. Nice. All right. So there's Horsehead and Flame Region. We're gonna save it and save exactly as seen. Not bad. Okay. So now, what we want to do now, I think, is go to we're going to go back to Sigma Orionis. Okay. Okay, and now what I'm going to do is I'm going to back out from Sigma Orionis. There we go. I'll tell you why, because now we're coming in at the same orientation from Earth. And now, let's do something else. I'm trying to find... Oh, here it is. The Horsehead. So there's the Horsehead. That's really interesting how the Horsehead looked. But again, the Horsehead is just literally a little area that protrudes from the cloud, and it'll vanish when we get behind here and it's not silhouetted anymore. It's right there, and it disappears because it's no longer being silhouetted. Kind of an interesting look. We're seeing all the dust from the galaxy through the galaxy center, because we're in one of the outer arms, where we are. We're kind of outer arm. And then we're seeing this beautiful ionized gas here. Really something else. So we come back around, and I'm not sure we'll keep the same orientation, but maybe. Yeah, we did, because there's the Horsehead right there. Right there, look at that. We managed to find it again. See that? You come with me, folks, you won't get lost out in space. I just got lucky, trust me. Well, there's the Horsehead again. So you see, it's just an illusory object that we see courtesy of Sigma Orionis here, that's causing this hydrogen gas to glow. And you saw that it's not just here, but it actually goes all the way around this, remember? See that? So it goes all the way around this. See that? That's all here and all throughout. There's depth to this. But there you go. All right, so now back.
Michael.
Huh?
Michael has a question of you.
Okay.
Says, could Mark talk about different temperatures in space, please? Max temp of OBA, FGKM, and nebula and supernova.
That's a really good question. O-type stars, we measure temperature on Fahrenheit scale, Celsius scale, but when we talk about stars, we measure it on the O scale. And stars that are O stars are going to be anywhere from 30,000 Kelvin to maybe 25,000 Kelvin. The B stars are going to be below that. The A stars probably around 12 to 15,000 Kelvin. You can look this up to correct me. I'm going from memory. The F stars, a little hotter than the sun. So we're talking maybe somewhere in the region of 11,000 to 10,000 Kelvin. Our sun is going to be in the range of 8,000 to 9,000. And then the stars below all the way to M, it keeps going down until you get to M, where the temperatures are between 3,500 and 4,500 Kelvin. Notice I don't say degrees Kelvin. Kelvin is the temperature. The Kelvin scale is the temperature. There's no degrees in Kelvin. And it starts from 0, which is minus 459 and change Fahrenheit. So it's pretty cold. All right, so this guy's done. This is good. I saved it. I'll save it as is, even though I did already. Is that what you want, Mike? You want more?
He said in space. I mean, if he's talking empty space between the stars, you're getting down. Well, you're well below 0 Fahrenheit. Empty. Well, I can't say that. Temperature is sort of empty spaces. Say
undefined.
Temperature is sort of meaningless, really.
It is, because if things in space either absorb radiation or they radiate radiation. So in other words, an object in space will absorb radiation and radiate infrared radiation. Okay, a dust particle, an asteroid, your body. Okay, And so that's what happens in space, because if you look at the ideal gas law, PV equals nRT, okay, it relates to pressure and volume equals N constant, R and T's temperature, okay? So it relates to temperature, pressure, and volume. Temperature and pressure, those are the big ones, okay? So if you have no pressure, you don't have temperature. And in space, there's no pressure. So you can't measure temperature in the same way. You can measure black body radiation. You can measure the radiation something gives off, and it follows a process. It follows a black body format, or should I say characteristic curve, right? So that's the thing that we look at in space. So you can only measure temperature when radiation is impinging on something, and thus that will absorb radiation, and then that can provide you with a temperature, okay? But you need to have a material that can absorb that radiation and then re-radiate it. And you don't need, you can measure the infrared radiation that's coming off of something and figure a quote-unquote temperature of the material, all right? But you can't think about temperature of a vacuum, which is kind of weird, temperature is only related to the medium that the radiation is moving through. And if it's not moving through a medium, if it's radiation alone, then that doesn't do it. Give you an example. Who's had radiant heaters? The quartz heaters, those little things that get hot, right? Did you ever notice that the air in the room doesn't get warm? Okay? You get warm because it's radiating radiation at you, but the air between you and the heater is still chilly until you radiate infrared energy back, warming the air. See? So I think that the point is, you don't, with radiant heat, you have to rethink how you think physics works, right? So that's something to keep in mind.
Michael asked earlier, what's the hottest things ever? And the jet streaming from a supermassive black hole. I saw somewhere a day or two ago, Michael, they think one of the hottest things they've ever seen. They saw just recently, they got some sort of, per what Mark was just saying, I don't know how relevant really a comparative temperature of this would be, but they measured, I assume in Kelvin, a white dwarf, the surface of a white dwarf, and it was much, much hotter than any star. If the O stars are like 35 or 40,000 Kelvin, this white dwarf was like 200,000 Kelvin. It was incredibly hot.
That's pretty cool. I didn't hear about that yet. All right, I'm going to take you to Betelgeuse. Why? Well, because I want to show it to you in 3D. Because Betelgeuse is a red supergiant, right? And there it is. And it looks round like any other star. But you have to understand that Betelgeuse, as a red supergiant, is going through a phase where it's undergoing these thermal pulses. And they're not even. There's bubbles coming out of one side of the star and then the other side of the star. And it's such a big star. If you put Betelgeuse where the sun is, Betelgeuse would go out to almost Jupiter's orbit. We're talking about a big star. So at that far out, even though it's still hot enough to melt you to a cinder instantly, it's not hot enough to keep molecules from forming. And so we will get molecules of dust out there and so forth. All right. So what I'm going to do is show you the image of Betelgeuse here. And Fantasy says our sun will reach Jupiter one day, a billion years from now. Not exactly, Fantasy. Actually, it's gonna swell into a red giant. It's not gonna swell as large as Betelgeuse because it's not nearly as massive. Massive stars can become these red, massive supergiants. There's even hypergiants. But the sun will probably expand as far as and maybe possibly engulf the Earth. So it won't go that much further. All right. So nothing to worry about there, except that you'll be, the Earth will be swallowed up. Kind of weird to think about that, isn't it, guys? That there will be a time when everything you know will just be cinders rendered back to the interstellar medium. Man, I tell you, we gotta definitely, get our UFOs and get our spacecraft, man. We gotta get our spacecraft out there and get ourselves off this planet. We gotta get off this rock. That's what we gotta do. All right, so here's Betelgeuse.
That temperature thing on white dwarfs, I wonder still really in a sense if it's kind of meaningless at that point, but a quick blurb I read said 180,000 Fahrenheit.
180,000 Fahrenheit.
Yeah.
All right.
Anyway, carry on.
No worries. All right, I'm just gonna take a picture of Betelgeuse just for fun.
Mark, excuse me a moment, please.
Sure thing.
Right back.
All right, we're gonna stack this. All right. All right, there's Betelgeuse. All right, and now those rings around it are a function of our system. Let me color correct this. Here we are. So there's Betelgeuse in our telescope, right? But the question is, what's it really look like? Now, we've had some tantalizing hints. We've been able to see Betelgeuse because we've been able to, as being such a big star, we've been able to do a process called interferometric analysis. And interferometry can allow us to see the actual size of Betelgeuse. And that's really something. All right. Now, what I'm going to do is show you what Betelgeuse actually looks like. All right. And we're going to do that in just a sec. So we're going to let this thing cook away here, but we're going to now come over and do this. We're going to show you that. That's Betelgeuse. And you say, well, how do I know that? Well, because I just went there. But let's now zoom in on it. Let's get a little closer. All right, watch this. As you get closer to Betelgeuse, all right, let's do this. Whoa, how about that? We got to go slowing down. Okay, as we get closer to Betelgeuse, check this out. All right, now we're noticing something odd about this. This is a star. Now, yes, we're not showing you the corona, the big, bright, hot outer atmosphere of the star. Okay, we're not showing you that. Okay, I know it looks sort of like Mars, looks like a rotting orange, I get you. But you see the bumps? Now, if we move just off to the side, let's see if it reproduces what I would hope it does. Yeah, it does. Now it shows you the dust that rings Betelgeuse that we see around Betelgeuse. Look at that. So there is a lot of stuff coming off of Betelgeuse that we see. Because Betelgeuse is a flare star. It's doing all kinds of crazy stuff. So what I'm going to do now is I'm going to show you this Okay, let's stop moving here for just a second. All right. I'm gonna show you because I want to get to this. Let's do this. So if we look at a star, stars' photospheres, or the upper atmospheres of these stars, they typically are very round, right? But you look at this elevated area. Now, no, this is not exact, but this is notional. But look how bumpy it is. This is actually very much how these red supergiants look. They're very bumpy like this. And again, they're putting out all kinds of flares and other material, makes bubbles in the surface of the star. I mean, look how uneven this is over here. You know? Very much what we know about red supergiants. Now just imagine Jupiter being like at the outer fringe here. Earth, you wouldn't even see it. It's just literally not even visible. So there we go. So let's but it's still bright. It's still bright to look at. We're using the ultimate welder's glasses here to actually do this little journey as we go over the surface of Betelgeuse here. And because it's a star, it's not. We're not actually seeing anything move because it literally takes hours for stuff to happen on a star. Just like with our sun. Look at this. Looks like we're going over mountains, but those are upwellings of hot plasma. So that's what's going on here. You know, that's what's happening here, and that's the fascinating world of Betelgeuse and Antares and any other red supergiant that's out there. That's what's going on in the atmospheres and in the realm of the red supergiants. And away we go. Farther away the better. Safer out here. There we go. So there you go, and that's kind of the gist of how these giant stars operate. And in our view here, this is kind of what we see. But we actually have done surface modeling of Betelgeuse through interferometry and actually saw its surface and the material around Betelgeuse. This is not that. This is just light artifacts from our system. Okay. Hey, Lisa Bocamp, how are you? Nice to see you. I think you were here for a while and I didn't say hi to you. I'm sorry. Yeah. So that's Betelgeuse here. So that's cool. And we're just going to save it anyway because it's kind of a funky thing to save and have fun with, right? All right. So now let's go to something else that might be fun to look at. And hey, Daryl.
Can I throw in there that Betelgeuse is one of the few stars we could actually see size in the star? It's not just a point of light.
Yeah, I just mentioned that. I don't know if you were away when I said that.
Yeah,
I was talking about the interferometry and stuff like that.
Yeah.
I mentioned how Antares is also. So that's pretty cool. So. All right. All right, so we're going to save one more of these. And then save one more of these exactly as seen. And then we're going to get out of this and go to the next object that's going to be fun to look at. Wouldn't that be
Because-
funny if it went supernova right now? Like, what'd you say?
Is it too late for the crab, or did you have something in mind?
No, I think we can go to the crab. I was gonna go to the Rosette, but let me try and see what
Oh.
the crab is.
Well, no, while you're in the neighborhood,
Yeah, I don't
We'll
want to
do the
lose the.
Rosette.
Well, we won't lose the crab. The crab is pretty high.
it's getting over there in the west now. You know, all the bright stars of winter are west of the meridian by midnight now.
Mm-hmm. They are.
So they're on their way, going away. Stars of
Yeah.
spring are in the east.
It's only 10 o'clock here, or there, I mean. But you're right. I don't want to dilly-dally. I'm going to center this cluster of stars. And bring it up into the view a little more.
In DC 2244, if I remember correctly.
I think you're right. This is called the Rosette Nebula. And we're going to just drop it down just a tiny bit and go a little bit east.
Boy, something's up with my YouTube tonight. It's not keeping up at all. It's every time I go to YouTube, it's not live. And
So you gotta
I
keep
don't see
hitting-
what you.
You got to keep hitting the refresh. Is that what you're saying?
I have to keep hitting the live button.
Okay.
I mean, that's why I've missed some of the stuff you showed in the Space Engine.
Okay. Tricia Ferrara says, Mark, I'm still wearing the hard hat after your asteroid presentation last week. That's funny, Trish. Thank you. And remember, if anyone wants to learn more about how to use the LRO quick map that I went through, I'll be happy to do that too. All right, this will be where we're going to stay. Now I'm going to go and we're searching. We're looking for a guide star. When we find it, here we go. 25,000 milliseconds, which is 25 seconds. Off we go. Go into our stack, and you'll see the last thing, which was Betelgeuse that we took. There it is. Yep. And we'll clear this. Betelgeuse is at just a beautiful orange color. Stars are very now. It's orange. It's so big because it's so far away from that central core of fusion that's going on that the temperature cools off. In the stars, the temperature goes from blue to all the way to red, and so that's what's going on there. Okay, this is the Rosette Nebula, and we're going to color correct first, and then we're going to do a process to make it look like it punches out. There we go. And this is the Rosette. Let me take this one and do it like this. That's pretty. Really pretty. Really pretty.
Yeah. I think a good coal fire is about as hot as Betelgeuse is.
Well, on the outside, yeah. It's many millions of degrees in the middle. In fact, it's,
well, sure.
you know, yeah, of course. And it's going to be fusing silicon in its core before it goes supernova. And when it fuses silicon, how about this? Here's one for you guys. When a star starts fusing silicon in its core, that process from billions and billions of years of the star's life, that process for all these big, giant, supergiant stars that make all the silicon we know, that process lasts only 1 day in the star's core. And silicon is the very, very last thing that it will make before it goes supernova. Interesting, huh?
I was off a little bit. Betelgeuse, 6,000 degrees Fahrenheit at the surface. Coal, I think, is... I'll have to look that up. It's not that hot. Maybe 3,000. I may have been getting my Celsius and Fahrenheit confused.
It's all right. Look at that beautiful. Oh, that's gorgeous. Let's
3,500 Fahrenheit.
let's just do a color match again. Look at that.
So never mind.
No problem. So here's what's happening here. This is a young hot star cluster, and it's carved out a cavity in the nebula within which it formed. So its stellar winds are pushing dust and gas away, making this big cavity in the center. And the stars are hot and are causing the hydrogen gas to be ionized. That is, the only electron that hydrogen has is pushed off the atom for a period of time because it absorbs ultraviolet energy from these stars. And then it collides with things out in the interstellar medium momentarily, comes back into the atom, and cascades down a bunch of energy levels. And the level it gets to most often, that these electrons get to most often, is the second level, n equals 2. And n equals 2, what happens is while it's dropping in, it's giving off light. When it gets to n equals 2, the light it gives off, because it's losing energy, it has to give up something. It gives up energy in the form of light. It absorbs light to jump off the atom, but then it gives off light as it comes back in. And the n equals 2 level is predominantly a light that's well up into the 600 nanometer range, and it's actually it's the red of hydrogen alpha, and that's why it's red. It's the most predominant color that you would ever see in the universe, next to perhaps a blue for a reflection nebula, or a green for an oxygen, doubly ionized oxygen. That's the Rosette. That's beautiful, isn't it? You know, I didn't know that we're going to get as good a night as we got. I'm really, really happy about this. Mike says, Mark, are we seeing gravitational lines in the red clouds in the bottom left quadrant? Gravitational lines in the red clouds. I'm guessing you're talking about these red clouds and maybe these things here. Actually, let me explain what the process is that might shape those clouds and these dark clouds and so forth. When these stars formed, they radiate a lot of energy. When you feel the radiation on your face from the sun, it feels warm. You feel that radiation striking your face. There's a force associated with that. Okay, now the sun is not a very powerful star relative to the bigger stars that there are out there, like O and B type stars and A stars. So an O star's radiation hitting your face, it'll chew through you in no time. You know, it's ultraviolet radiation, which is most of the radiation given off by O stars, right, is going to be a death beam, okay, for you, right? So this radiation for these young hot stars is pushing out material, pushing it away. And that's what's shaping what we see in this nebula. Dense regions like this up here. Okay, let's move in on this for just a moment. Okay, we look at dense regions like this right here. These dense regions are being shaped by these stellar winds, most likely from these stars. However, because they're denser, they're particles, they're not gas. Particles are obviously a lot more massive than gas atoms. Particles are molecules, right? And so these don't move as readily as the gas does. That's why the opening is cleared out of any of the hydrogen and the oxygen, right? But the gas is cleared to some extent, right? But you'll notice that the dark material here is lingering. Yes, it's being shaped by the radiation, yes, but it's able to withstand it for a lot longer and for a lot more capably than the gas can. This is a Bach globule. This is a Bach globule. What are those? Those are areas of self-condensing, gravitationally coalescing dark material that may eventually become a star or a star system with planets eventually. Now, the benefit of these Bach globules is the stellar ultraviolet radiation coming from these hot stars may not be able to reach into these Bach globules, and that dust will actually protect anything that might form in there. So that's what's interesting about these dark regions. And I've told you this before, life begins in earnest in those dark regions. That's the most important regions in the universe, are the dark regions that are actually black. What time's the moon rise out there? I'm seeing a blue cast. I'm wondering if the moon is up.
Let me look. Probably about 9:45.
Yeah, because I see a blue cast.
I think it was 9:12 p.m. here tonight at moonrise, and you're about a half hour behind me, sky time.
Okay. Yeah, so I suspect the moon is up.
9:12 here.
Okay.
Wickenburg, 9:47. So yes, the moon is up.
All right, I recognize a blue cast. If you notice in the image there, you can see a blue cast. So that's why it's happening. Let's see here. All right. Okay, that's beautiful. All right, I'm going to compensate for this blue cast by dropping down some of this. There we go. Isn't that beautiful, guys? This is such a complicated region. Such a complicated region. Yeah. Lubo says, I'd love a focal length 200 millimeter f2.
Oh. Focal length 200 millimeter.
What's that?
I thought he was talking aperture 200 millimeter. Focal length 200 millimeter, that's not very much.
I think he wants to do. I think he wants to do like a wide angle type nebula photos.
Yeah, he says a little CubeSat. My mistake, Lubo. I thought you meant 8-inch aperture f2, which would be an 8-inch hyperstar. I remember you talking about an 8-inch hyperstar earlier.
Yeah.
8-inch focal length, though. I mean, that's 200 millimeters. It's not a lot.
Wow, this is looking pretty. I'm amazed at the detail that's showing up here. It's actually, for all the clouds we had out there recently where we couldn't stream, I gotta say, look at the detail in here. There's a lot of detail. Look at these pillars. You know, I've talked about these pillars before, guys. Like, you have these young hot stars, and I just mentioned how the dust is more massive than the gas. So the dust will stick around and be able to weather these stellar winds. So what happens is a dense area of stellar, well, I'll just zoom in on this, a dense area, right, like up here, right here at the top of this little stalk that you see here. Okay, this area of density is dense enough so that these hot stars can't push away the material behind it, because it's protecting the material behind it. So that's why we have a stalk behind it. That's why we have a stalk behind this one.
Yeah, both those stalks are pointing toward that star.
As they should. They should be pointing toward the cluster in general.
Yeah.
You know? And we see that with a lot of these stalks. They actually point toward the stars in general. Now, if we come up here, look around the other side, here we see the same kind of thing. This is pointing right at the star cluster. That's no coincidence. This is pointing at the star cluster. And it's no coincidence that this is very dark. This is a high-density area, an area that can withstand the pressure, the solar stellar winds, the impressive radiation being sent out in plasma form of high-energy protons and electrons that are streaming toward all this material. Same here, a dark area here, a dark area here, weathering the storm. The lighter stuff is maybe blown back a little bit and sort of dismembered a little bit, but this dense stuff at the leading edges and these areas here have stuck around and has had the ability to stick around. So it's interesting how this works. There's another one right there, you know, and this one trails back in this little tiny stalk here, probably because again, we don't know. This is not a 2D thing, and to see this, we're not gonna see this in the same way. While this is, we call this integrating when we're actually building an image like this. All right, so while this is integrating, what I'm going to do is zoom out, right? And I'm going to, right now, do one thing. I'm gonna drop down a little more of the blue and get us to, drop that blue and a little bit of that green. Get us back. Now, see, that's a little more what it's supposed to look like. All right. And while we're waiting for that, while that's happening, why don't we head over to our stellarium? Because this is what it knows as the Rosette Nebula. Okay. So as we approach the Rosette, again, we don't see that impressive cluster of stars, do we? We just see these tiny points of light, all right, that are the stars. These are the points of light. Now we are actually inside this, we're inside this cluster. So now if we move around it, okay, this is what it looks like inside, which is kind of cool. At some point, I imagine that there will be enough data, 3D data, to actually backfill what this may actually look like with even more detail. But that's the hot young cluster inside. See that? All right, so now we actually are... We're actually in the middle of this, right now we're in the middle of the nebula. So we keep going around. So that's our 3 view of this particular area. And we'll come back to approximately where we were before. Right like that. So it's pretty close. So yeah, so this is a little bit more of a it's a nice exercise to be able to show you the 3-dimensionality of the universe. Now from here, if we look around, what else we got going on here? Well, we can't tell what's going on because we're here at the Rosette Nebula. We don't know, but all that we can know is you can't recognize things. However, if we say, well, wait a minute, where's Earth here? What? I just want to know where the Earth is. Oh, the Earth is over there. And it's 4,600 light years from here. Right? Here's the dark dust. All this dust in our galaxy was made through supernovae explosions of red supergiant stars. That's all that material in the outer atmospheres, that's all material that's blown out in a supernova. To another, perhaps equal extent, maybe more, stars like the sun, when they die, they slough off their outer layers, and in those outer layers, planetary nebulae, as we call them, you can get dust forming out there. We see lots of, beautiful green glows from doubly ionized oxygen, like in the Dumbbell Nebula, and red in parts of the Dumbbell, and in the Ring Nebula, and in others. And so there's all kinds of phenomena in the universe that would just kill us if it had the chance. Okay? Being near a hot young star cluster, like in the middle of the Rosette, that'll do it. Okay? Unless we are inside one of these beautiful regions inside the Rosette, where we have a dark nebula protecting us, right? A set of dark material. So that's something. Yep. You notice the seconds ticking by so quickly right there. This system pauses when we're doing the view from the other program, Space Engine. So now we're back. It's kind of funny how that works. All right, so there we got this now. So what I'm going to do is bring up our stack again, and because the lunar light keeps getting added to the image, I have to keep correcting for it. But there it is. So while I'm here, I'm going to save this. I've got plenty to go crazy with. Save exactly as seen. Here we are. Let's explore. We're going to come up here and we're going to go up to the Bach globule region again. But we're going to go right up here. Look at these beautiful details here. You can actually see almost three-dimensionality in these structures now up here, which is really cool. Now we move down, and there's regions where the hydrogen gas is a little more dense, so the red is richer looking. Same here, okay, as in here. And then we have walls of dark nebula in here that are interesting, and little tiny details. These are details, Daryl, that we've never seen before, right here. Details in here. You can zoom right in. Wow. Interesting, even though we're looking through light clouds, it doesn't look bad.
Yeah.
And probably on the other side of the cavity here is this material here. So that's really neat. Let's zoom out. All right, so there's the Rosette. This dark line down here is the guiding corrections. It's moving a little bit up in declination, as in up and down, for each shot to correct. Very nice. Really something. Let's bring this back now. Dock this back up here. Okay, like that. Let's save it another time. And say, okay, save exactly as seen. Wow. So, guys, let me know if you like the 3D forays that we are doing here. Hopefully you do. I'm thinking it's pretty cool. But I need to hear from you. I want to know what you think. So let me know in the comments, please. All right, let's see now. I guess we're gonna... I know I'm gonna do this. I'll do this. We've done the Christmas tree cluster a number of times. I think I will do this and we'll check it out. So this is done. We took I'll do one more save. Save exactly a scene. There we go. Off we go. And now off to our Christmas tree cluster, which is highly inappropriate right now because it's not even remotely Christmas. Mr. Django, thanks for spending some time with us. Great to see you. Thank you. Hey, Sam S. Sam S says it's great. He thinks it's great to help visualize. Good. Because I'm planning on using it for a lot of the streams now to help visualize what's going on. You know, not too much of it, just enough to show the things we're looking at. You know what I mean? Which is really cool. All right, so let's now go and do our run to this guy. We're going to run over to the Christmas tree cluster and the Cone Nebula. You'll see the telescope is pointing pretty straight up right now, so this is good. Here's the Christmas tree cluster, and the cone is right down here. So we're going to move down a little bit and move to the west a little bit. And I think we should continue to go down just to see the Hubble's Variable Nebula and see what state it's in at the moment. We always check it because it's a variable nebula because it changes its brightness, which is really cool. So we have to keep going. Okay. Here it is. With our with the other camera on here, we were able to see 2 degrees by 1.5. Now we're at 1.5 by 1, so it's a smaller field, and we got almost twice as many pixels in the camera. So this is very, very much higher resolution in the end for us. So it's really nice. All right, well, there's Hubble. Lisa says we're all galactic. That's why we love the stars. Yeah, you're right. We're made of the stuff that came from the stars. Everything in your body was once made in the core of a star. Isn't that crazy? Cosmic Ray, thanks for reminding me, because I had mentioned before for Izabela we're going to do this because she wanted to know what it'd be like to go through a globular cluster. So I will do that after this. That is absolutely what I promised her I was going to do, so we're going to do it. All right, we're going to get this aligned again, and then we will... Okay. It's a little higher. Why am I doing this so carefully? Because there's a nebula out here that we want to catch at the same time. There's one over here out more called Dreyer's Nebula, which is beautiful. So I'm just going to do one more little jog.
You see the Christmas tree now. It's upside down. The bright star is the base of the tree. The point of the tree, the top is toward the bottom of the screen.
Right here or right here, I think. Right by the cone.
In that area.
Yeah, and then there's the side, the base, the stump. Yep. In the southern hemisphere,
pointing down.
Yeah, in the southern hemisphere, the Christmas tree is right side up. Okay. Let's we got our guide star. Let's do 25 seconds. And pop out of here. Jump into our stack. Clear the last Rosette, which is up on the server now. And then we'll make this one as a Christmas tree nebula. Okay. Let's check this out. Oh yeah, the moon is up. But look at that. We'll correct for the colors, but there's the Christmas tree. And here's the Cone Nebula. That is beautiful. Let's see what we get when we correct it. Alright. Look at that. That's nice. Let's come on down here and look at the Cone Nebula. Is a dark nebula. That's LDN 1613. And what I'm going to do is Christmas tree cluster 2264. All right, 2264. Now let's go and bring this up to just near the top to help make this look a little more three-dimensional. That's pretty cool. Okay. Really pretty. So this is obviously a molecular cloud here. You can see there's some really faint diffuse hydrogen that's actually being ionized here. You'll also notice a very strange looking color and nebula near the top here, and it's no illusion, you're actually seeing that. It looks a very different color from the reds over here. That's because we're looking at a combination of dust and gas, and the dust is scattering some light, the starlight, which is blue, and where there's more dust than there is gas, hydrogen gas to be ionized, it'll look more blue. but where you have a mix of hydrogen gas with the dust, then what happens is you're getting some of the hydrogen being ionized and some of the light being scattered by the dust that's in here mixed in with the gas. So you get this really interesting color, kind of like the inside of the Running Man, which is sort of magenta, because that's what happens with light when you mix blue and that red. So we get this interesting dichotomy of color between these and this area here. This nebula right here is known as the Phosphor Nebula, and this is not a glitch up here. This is actually a very dark nebula up here, which is really interesting. Little color correction there. What I'm going to do is bring this is the dark level. If you come way out here, it'll look light, okay, because you're going to mix in other starlight and moonlight. But if you ride this curve up, when you get near the top, you're not losing any data when you get up here. But look how beautiful that looks. The Christmas Tree Nebula. Hey UFO bro, what's up? He says it's so sad that as individual citizens we can't afford to have the mechanism isn't in place for us to have our own telescopes in space. Guess what? That's going to change. I actually predicted that there'll come a time when, and it'll start with universities, and maybe it's already with private corporations, but with universities, they're already making satellites that they can put in space. CubeSats are an excellent example. And the CubeSats last a few months in orbit, and then they return to Earth and burn up. So orbital real estate is really quite expensive, because you have to plan out every last detail to the point where you can't put something up in orbit unless you know what will happen 4,562,322 orbits from now, what it's going to do if it's still up there. So there's a lot that goes into it, a lot of computer modeling that has to take place to make sure you're not going to collide with anything else up there, ever. But the reason why, as individuals, it's hard now is because, first of all, money, of course. And space isn't really accessible to even the richest of us yet. We need to spend gazillions of dollars, hundreds of millions, just to launch and put ourselves into space. If we could do it at $75 a head, we'd go already. But the thing is, one of the problems is that space isn't accessible to everybody for another reason too, and that is that if it was, there'd be all kinds of junk up there, and that junk would be enough to possibly trap us here on Earth. If you had every college student put a CubeSat up, okay, and then a corporation decided to throw up 3,000 CubeSats along with a bunch of other satellites, and Elon Musk said, I'm going to add 32,000 more satellites. What will happen is that you're going to end up at a spot where the clear paths to orbit may not exist at some point. And so what we have to do is start clearing the old stuff out of the way. And that satellite reclamation process, booster reclamation, that's all stuff that NASA's trying to think about. And they'll do it. They'll do it because they're going to have to. The point will come where they're not going to be able to launch off the Earth for safety reasons. And if they get to that point, they weren't thinking, because they've got to have a reclamation plan in place before that time.
There is a name for that. Escapes my mind at the moment. Where it'll get to the point it's so crowded up there that they'll start colliding and causing more junk, which causes more collisions, and it's like a cascade failure, and we'll lose the ability to go into Earth orbit.
Yep, that's the idea.
What's the name of that?
I don't know the name. I know what you're talking about. That's what I was just describing as a
Yes, I know.
a possibility.
Which made me think of it.
Yeah.
It has a name. I can't think of it offhand. Let me see if I can find it.
Now, Calabos, who actually works at SpaceX, says that's why we constantly monitor the sky for any objects that might collide with our Falcon 9 or Falcon Heavy rockets and soon our starships. Yeah, I'm absolutely certain he's right. You're absolutely right about that. Lisa Beaucamp. Plus, the mothership needs room to come pick me up. There you go. That's actually funny, if not just a little true.
Kessler syndrome.
Kessler syndrome?
Yeah, Kessler syndrome.
Okay.
Cascading series of collisions between orbiting satellites and other objects could take place if a critical mass of space debris is allowed to accumulate in Earth orbit, dubbed the Kessler syndrome.
All right, that makes sense. That makes sense. All right, so what are we doing right now? We're actually, this is the Christmas tree cluster, which doesn't look like much here, but this is because we're looking at realistic stars. If we look down here, this is the Cone Nebula. Right now,
there.
Yeah, there's the cone.
The cone is to the upper left of that.
What are you talking about?
That dark cone-shaped thing in the center of the screen.
I don't. This is don't get confused with the Milky Way back here.
No,
Let me.
right in the middle of the screen, there's a dark cone shape pointing upwards toward.
Right here.
No. I can see your cursor and you're below it. It's dead in the middle of the screen.
Here?
Yes, the Cone Nebula right there. You don't see the cone shape?
I thought this is the cone, because that's going with it.
Are you depending on Stellarium to tell you that? Because I saw that when you were on Stellarium. The name Cone Nebula was offset to the lower right of the cone. You got the cone
Yes.
dead center of the screen.
You think that's the cone?
Yes.
I don't think so. I mean,
I
Again-
bet you $1.
$1? Why would I risk that kind of good money? Well, I actually see a cone shape right here, though. There's a cone right here. So is that supposed to be the cone?
Where are you at?
I think that this is the fox fur, and this is the cone right there.
Can you back out?
Yeah.
The Cone Nebula sits at the very bottom of the image of the Christmas tree, which is pointed upside down. It's at
Yeah.
the top of the tree. That's the cone right there.
Where, this? This is the cone.
It's the Dark Nebula.
Yeah, this is the dark nebula right here. I think that's the cone. you're seeing it up here, and I'm seeing it right there. Well, you know what? It's not gonna.
I'm gonna drop this in your chat.
Okay.
Okay, there it is, right there.
Oh, you're in the Skype chat you did?
In our chat, yes.
That's okay. Let me see what you're talking about. Okay, I'd like to see what you're talking about, but I can't. All right, hold on.
Here, I'm going to send you the picture itself. What I sent you was the article.
Oh, article for what?
The Cone Nebula.
In Space Engine?
In our Skype chat.
Okay, okay. I can't get to the Skype chat. Why not? I don't know. All right, so. Well, first of all, let's go back here so everybody can watch the cone being built. All right, and then we'll come back here. Let's see here. Knock out some blue. Knock out some green. That's more like it. Hey, Lisa, thank you. Very kind. Here you go, $1 and breakfast in the morning. Great show. Thanks, Lisa. That's very sweet. Thank you so much. All right.
I posted a link in a group chat for the stream. And it is the picture of the cone at the Wikipedia article.
Well, okay, I'm not sure what that has to do with the space engine view.
Are you on Space Engine again?
No, I'm not. I'm back. I'm in this. I'm actually trying to get to the chat. I can't see a chat for this now in Skype. I do not know why. Maybe because this is the problem.
From the YouTube page?
Okay. Yeah. No. You said you sent me something in our YouTube chat. Now I'm there. I figured it out.
No, not in YouTube chat. In our Skype chat.
No. Yeah, I got you. Yeah, that's exactly right. I want to make sure that for some reason you weren't on the same page as I was, because in Space Engine, I was pointing out where I thought the cone was.
I never saw the Space Engine.
Oh, well, that's what I was talking about the whole time. I forgot you.
That's what I was saying earlier.
It.
I keep losing.
Okay.
Let me refresh again.
No, it's okay. Because right here, if you look at my screen right now, the YouTube screen, I know that's the cone right there. And I know this is the Christmas tree cluster. I know this is the fox fur up here. So I know that. So,
okay, well, I was looking at the Skype window you're sharing. I could see your cursor moving, but you were well off the cone in the image that was not being shown.
That's why there's confusion, because I was actually moving within Space Engine, but you saw the cursor still moving. Okay. Yeah. All right. Yeah, I couldn't share that. Okay. Never mind. Error, Will Robinson. Oh no, we're all gonna die. Be quiet, Dr. Smith. Yeah, this is pretty cool.
You know, I hated the movie Lost in Space. I think it was Gary Oldman. Gary Oldman played Dr. Smith, and they had to turn him into a big giant spider or some kind of silliness.
The movie? What movie was that? Oh, wait a minute.
Yeah, they did a movie Lost in Space.
The more modern one where the robot was not what YB9 looks like, but some fanciful looking weird robot, right? If I recall.
I don't remember the robot in the movie. The original TV show, it was Robbie the Robot, wasn't it?
No, not Lost in Space. It was the YB9. Okay. And then what's funny is, Irwin Allen made a lot of interesting, crossovers. There were episodes in some of his fantastical shows which showcased things you've seen in other of his fantastical shows. I think Robbie the Robot was in Lost in Space for an appearance in an episode for something. And I don't remember what, because Robbie the Robot was for Forbidden Planet.
Well, that was the first place. I mean, Robbie the Robot really made it around. In Lost in Space, it was Robbie the Robot. He probably had a different name, but it was still Robbie the Robot. You know, the robot itself. Danger, Will Robinson, danger.
I know that was YB9. That was a very different robot than Robbie. Robbie had that conical head, and the robot in Lost in Space had that oval plastic top of his head. Remember?
I think they were in both movies. Never mind. We're beating dead horses here.
That's true, because everybody in that series is almost dead. Only Billy Mumy is left behind. I think everybody else is gone. Jonathan Harris died a few years ago. And for those of you that know the show, Resident Alien, it starts again in February. And you're going to recognize the voice of a gray alien in there. It's none other than George Takei, Sulu from Star Trek. So, the Greys talk like this. Ha, ha, ha. It's obviously George Takei. I'm not sure what they did there. Yeah, see, Sam S. says that Robbie did make an appearance in Lost in Space. I kind of remember that. But he wasn't a regular, of course. But the YB9 robot was the one with the, or B9. Okay, yeah. He had like the corrugated legs.
The very head was different, but the body was the same in both robots, I believe.
Maybe I have to look and see.
I'm looking at him right now.
Yeah. Yes, Ronald. Billy Mumy is still alive. Okay. Christmas tree gets saved like this. And saved exactly as seen. That's beautiful. Really pretty. Okay. So let's take one more look here at this before we get. Oh, that's not going to work, is it? Let me get rid of this. And get rid of that. See if it's still there. The buffer may have been cleared. Oh, good. All right, yeah, so here is this beautiful wispy Phosphor Nebula up here. Hydrogen and dust comes down here. Then the dust is more dominant over the hydrogen, if there's any in here, and scatters the blue part of the spectrum of the starlight. Mixes with more dust and hydrogen gas, giving it a subtle red glow as well as a brownish glow. And then down here it's more hydrogen gas than anything else. And then this is all dark nebula down here. Then at the top, for another time, we'll photograph and process what's way up top here, this dark area. It's actually a very dark area that shows if we pull this back just a little bit.
IMDb.com says the guest star was Robbie the Robot from the movie Forbidden Planet and was used as a model for designing the Lost in Space robot.
Okay.
So.
So I'm not sure if you made your point.
B9 was derived from Robbie the Robot.
Okay, that was the order. That's fine. That's cool. Look at this here. You can see the dust. You can see the dust here, and then this little tongue of dark dust which goes up. So, again, in 3 dimensions, with a better set of data, we'd be able to model this whole region and see all the intricacies of this region. But it would take years to build such a model, just for this one little area. Wow, that's pretty cool. All right, so now let's go back to, and let's see. Oh, we got a satellite. There's Dreyer's Nebula right there. Whoa. Dreyer's Nebula is not really represented in the 3D universe here. Let's see which is best. Okay, I want that.
Excuse me just a moment, please.
Okie doke. Alright, I'm trying to just locate exactly where we are. I guess I'll just take a shot and see. Clear it, do that, and now when the next one comes in, we'll know where we are. Oh, that's pretty good. Well, even the moon out is looking good, so we're gonna continue this one.
This Dreyer.
Yeah. Okay. And this will be the last object for tonight. As I said before, Dreyer's is not well represented in the space engine world yet. Jessica says, Robert Kinoshita passed at age 100, designer of, was it Robbie the Robot? That's pretty cool. I'm guessing he was Japanese. That's why that robot always reminded me of Godzilla. Like that kind of era. That's neat. So Dreyer's Nebula has lots of colors and beautiful interplay. This here is, this red is coming over from the Christmas tree cluster, which is out here somewhere a little more. We've just moved over to that region. And with some care and the no moon, we can actually take a bunch of photos and end up making a nice mosaic of this region. Hey Curtis, welcome back. And Calabos is, as always, saying wonderful things about joining us. Hey, Izabela! She was, hey, oh my God! Yeah, this is the last object, though, Izabela. See, I'm glad you got here before we ended. I am going to do one thing for you, Izabela, and I'm glad you're here now, because now I can make this happen. Which I think will be really cool. Yeah, I did say it was the last one, didn't I? But it's not the last one.
Yeah, I never heard that one before.
Yeah, I know, right? Okay. This is Dreyer's Nebula, Izabela. Yeah. Yeah, fantasy. Yeah, we're doing one. Well, not another shot. I'm going to take us on a ride to a globular cluster because Izabela has asked for that. Oh, and thank you, Izabela. I'm going to do that. She just told me something I had meant to do.
Calabos says, please, no. He doesn't sound very convincing, though.
Yeah, I know. He's all right. But once he knows that with the wrench you're able to post links, that might be very helpful moving forward.
He says, seriously, he'd rather not.
Okay. I do understand his reasoning, so...
Well, he's more than earned a seat at the table here.
Oh, he has. Yes, he has. With no doubt at all. And he knows that. And so it's just, it's just his choice. Okay, I'm going to name this Dreyer's Nebula.
Maybe he's bashful.
He is. Yeah, Ronald, you have gotten quite a handle on Mixler. 113,000 total listens, not bad. Curtis Horn says, by the way, Mark, I did a follow-up talk at the last APEC where I went step by step. At the end, I realized 99% still are not fully with me, and it'll take time. Well, yeah. Curtis Horn's a very smart guy, guys, so he's, it's not easy to get points across to people that you have to kind of give them lots of background. Sometimes that's a problem. And so I've been there.
Heck, when I did public talks, if I could see that I got through to one person in the room, I thought it was a good night.
Yeah, I get it.
You see them out there, and you'll see a light go off over somebody's head.
That's right.
They have that aha moment, and
yes, the epiphany.
I figured if I had one a night, it was doing well.
Yeah. All right. So what we're gonna do right now is we're gonna, while we're integrating this, we're gonna cut over to our space engine, because now what I want to do is take us to an object that I think Izabela might like to see. So here's where we're going, Izabela. We're gonna head into the galaxy here. All right, and I'm gonna take down the number of light years we're going. All right, there we go. There we are.
M22, my favorite.
That's why I'm doing it.
Oh,
I figured Izabela would like it too.
sure. She better.
So there's the galaxy up there with its dust. These globular clusters are halo objects. They kind of sit outside the galaxy and go punching through the disk of the galaxy. And that's what we see. We're starting to see a hint of something in the distance, so as we close in, we're moving closer and closer. As we go by a star that goes too close to us, we temporarily lose the images of the detail because the stars are so bright. We had a star go by that was pretty bright there. So we're blasting our way through. All right, and here we go. Counting down. Oh yeah. So M22 is down here. It's actually outside of the main disk of the galaxy. It's a halo object down here, right? But if we actually move our way into it, right, you'll see something really interesting. You can find your way inside this cluster and see what it might be like to be on a planet inside this cluster. The problem, unfortunately, is that these clusters probably don't have too many planets. All right, but this is the journey inside Measure 22. So come along for the ride. If you look around out the windows, you'll see some stars going by.
When
there.
the distance is 0, is that when you're at the center?
Yeah. I gotta do this. But isn't this interesting? Because, you know, I just find this to be fascinating. We're inside this thing. This is what your world would be, your universe. Look at this. From inside a globular cluster.
What does that pointer mean?
That pointer was just where we're looking at the time. If I understand you. So we still go a little further along, right? So you'd have a lot of bright stars in your neighborhood from inside a globular cluster, as you can see. That's pretty neat. Many of these stars don't have a whole lot of metals in them, meaning anything heavier, much heavier than hydrogen and helium. So they're probably very pristine. They're actually some of the earliest stars to form, and some of them have been around here nearly as long as the universe itself. So they probably don't have many planets, but because these are collections of stars, gravitationally bound, all orbiting around each other within this cluster, they do move through the disk of the galaxy that you can just see through here. And as they move through the disk of the galaxy, they may shed some stars and may gain some stars, which is very fascinating. But this is a beautiful, actually stunning, view from inside a globular cluster. And as we back out, I think the most interesting location would be is if we were right just on the outside of the cluster, on the outskirts, and the cluster took up a third of our sky. That would be pretty cool. So you look at this. This is a huge number of stars to be near. I don't know cosmic ray. I assume that all of them are roughly spherical. They all have their little idiosyncratic paths and turbulent eddies. But yeah, so this is really pretty. So now it looks like the Measure 22 we know. Curtis, thanks for coming, man. Good to see you.
M22 is the globular that sits just above the junction of the top of the handle of the teapot and the lid of the teapot.
Mm-hmm. Kind of looks like the Pleiades from that Star Trek episode. We call it Tranya. We hope you relish it as much as we do.
That was Ron Howard's little brother, wasn't it? Clint Howard?
Yes, it was.
Yeah, I remember that.
Yeah. Very good. Well, there's a visit to a globular cluster, and that's for Izabela. Because she asked last stream, and the computer blew up when I tried to actually take us there last time, but I fixed that. Here we go. So if we come back to our sky tour, hey, look at that. I lost my video.
I still see it.
You see that, but I'm talking about my I lost my my operations cam. It's all right.
Is this what happened to you at 2.5 hours the other night?
No, this is very different. Yeah, that's okay.
You know what we're going to have to do sometime?
What's that?
Oh, check out M13 and Omega Centauri.
Oh, yeah.
If you really want to get in the big globular.
Yeah, that's very true. Well, it's okay.
So,
Oh,
are you still
interesting.
operational, or what's going on your end?
Oh, yeah, we're fine.
Oh, I thought you said you lost your video.
No, I lost my camera, but we're still running here. We're fine.
Oh,
Yeah.
the interesting
Yeah,
little
we're-
dark cloud there in the lower part of the Dreyer Nebula.
Right there?
Yeah.
Yeah, really interesting. Let's see if we can pull out a little more detail. First, let's do this. Oh, yeah. All right, now we'll punch this over. Oh, that's nice. That's Dreyer's. We're going to save that and save it just as you see it. Oh. Very cool. It has been a long stream because I wanted to, do this. I did. It's been. We've had a strange set of storm fronts come out to the observatory, and I'm just tired of them.
Yeah, I said in Skype chat earlier that I wonder if that's a manifestation of the El Nino, where the weather patterns are supposed to be farther south than usual.
Yeah, it might be.
I know you really been getting hit by clouds down there. Seems
I know
like
it.
much
And
of
it's
the
like-
winter.
Yeah, and I didn't like them. I don't like these clouds. Go
No,
away.
it's
Don't come
Been
back.
clear as a bell here. Sometimes at least.
Yeah. Mm-hmm. Oh, that's pretty. Okay, we're going to do one more exposure. All right, good. That's good, good. And we'll save that. I like doing streams on the backside of the moon, kind of a thing, you know. Backside of the cycle. There we go. Wow. So that's Dreyer's Nebula, guys. And that's going to do it for us. This has been a long stream, and I'm happy we could pull it off for you. So I hope you guys enjoyed that. And I am looking forward to doing something with you again as the moon wanes even further. We're going to come back and do a few other things. If you guys like the three-dimensional additions, again, let me know in the comments or in the chat, because those comments will be there forever. And I'd like to continue that, possibly. But right now, what I'll do is I'm going to shut down. And what I'll do by shutting down is I'm going to park the telescope. So I'm going to move the telescope to its shutdown position. There it goes. And you'll see the telescope moving down to its parking lot spot. So it's almost there. It's now pointing at the wall, which is why it looks that way. It's off. I can turn the scope off. Boom. And that cuts off the power to the camera and to a few other things. So now we can take this down. And this. So there you go, guys. I hope you had a good time. And we will be back hopefully on the next clear night. So I hope you guys have a good night. Thanks so much. And we'll see you on the other side. Good night, everybody.
Good night, everybody.